Hello, welcome. Yes, yes, just in time. Just in time, I managed to do that. Yeah. So I was waiting for my kettle to finish boiling the water, and I had only 1 minute and it didn't finish the boiling the water yet. Hello, hello everyone. Welcome to another Zozing stream. Welcome, welcome, welcome. Hello, 9-year-old PS Comp Size, 23, in CMH, Herzenplotzem course 64, 69, yet Anasov, out 9, hello, Hirose, CMG 69, Zozin, Herzenplotz, it's the same people, hello, Witness, hello, welcome, Slav 11, Kolumbetka, hello. So, yeah. Today is Monday, and that means today, according to the Skidoodle, we're going to be continuing the virtual machine in C. You can find the source code of this project here. It's a very interesting project, not gonna lie. So the idea of this project is to develop a virtual machine in the sense of like virtual machine for a language, like JVM or something like that. Right, that we're gonna use for our implementation of a Lisp, right? So it all started with the Lisp project. We were trying to implement our own Lisp language, and at some point I decided, well, we need to have our virtual machine for the Lisp to speed things up and stuff like that. I also wanted this virtual machine to be JITed. So, and that spawned a completely separate project that is called BM, right? So this is a virtual machine for our Lisp, but it can be used like separately from Lisp, so it's actually like self-contained thing. Yep, and today we're gonna continue developing it. Let's take a look at the current progress, I suppose. So let me start Team UCAS and go to the BM source code, and let me see, well, let me take a look at the status. I think I'm on a branch that is already merged, so let's check out the master. Hello, the Soul Sika. Welcome to the stream, and let's fetch everything. Tinux. Haha. Merge origin master. That's a lot of shit, not gonna lie. Yep. And let's rebuild everything. First, I'm gonna rebuild all of the executables, and then I'm gonna rebuild all of the examples. There we go. So here is an interesting thing. Our toolchain of our virtual machine consists of, I would say, 4 components. I think there are 4 important components. The first component is the library itself, which is just a header library. 25 kilobytes header library. It's actually kind of small, right? It's actually kind of small, and this is the whole virtual machine. 888 lines of code. How about that? So yeah, this is the whole virtual machine, seriously. But it cannot do much yet. I mean, technically it's Turing complete. If you think about it, technically it's already Turing complete. It has infinite memory. It what the hell is going on? TCM's G69 hello, subscribed with 2 months of Twitch Prime subscription. Thank you, and welcome to our epic virtual machine club. Isn't that amazing? How does it feel to be part of the virtual machine club? Feels good. Anyway, so here's the whole thing, and yeah, it's already Turing complete, and if it's Turing complete, I can program in it. Anyway, so it has infinite memory, it has conditions, and it has loops. What else do the fuck you need to have a Turing complete system? Anyway. So it's Turing complete, but we're lacking some useful features. Yeah, we need FFI, exactly, we'll need FFI at some point, and I will think how to implement that. It would be kind of cool to be able to, you know, DL open like C libraries, like SO shared objects libraries, and then do something with them. But I'm not sure if we're gonna try to tackle that like right now, maybe a little bit later. maybe a little bit later because it feels like out of the scope currently. So here's the first component. The first component is the library itself, right? And the three other components are these executables, BASM, BME, and DBASM. Okay, so we have, on top of having our virtual machine, right, that has its own bytecode, right? It has its own bytecode. And since it has its own bytecode, it also has its own assembly. That's right. And you can actually program in that assembly. So it's usually needed for debug purposes, right? So, and this is how it looks like. It's a stack machine. It doesn't have any registers. And yeah, so this is one of the examples that were contributed by one of the viewers. And this just calculates pi number over 750,000 of iterations using Taylor sequences, I think that's what it uses. Right, and so you can compile this example using BASM, right? So I think you have to provide the output, and there you go. That created a binary file. So the binary file is actually 416 16 bytes. It's pretty small. Igorovich, thank you so much for tier 1 subscription. Thank you, and welcome to our epic bytecode club. Thank you. All right, so it's actually pretty small, and it's literally just a bytecode for our machine. We can take a look at the hex dump. So this is how it looks like. It consists primarily of zeros. That's how epic our virtual machine is. Still smaller than elf executable. Yeah, elf executable is primarily just garbage. 98% of them. And then after that you can try to execute it. So BME is a virtual machine emulator, right? It's a virtual machine emulator, and you can just go ahead and emulate the executable that you just created, right? And after some time it will spit out a pi. How about that? So it took it to, like, how much time did it take? It took it like half of a second to compute like a pi number, which is not bad, I suppose, and it just prints the current stack of the virtual machine. So right now it doesn't have really that many ways to interact with real world. So what emulator does, it just spits out the state at the end of the execution before halt, and yeah, pretty much it. It's pretty much it. And we also have DBASM, which is essentially BASM disassembly. What it does, it takes the bytecode and turns it back into assembly in case you want to inspect it. So yeah, so this is how it goes. So I'm gonna do DBASM, whatever we just compiled, and here is the decompiled version of it. As you can see, it doesn't have any labels, it doesn't have any floats or anything like that, but it's still the same program. If you actually put it back into assembly, you will get the same program. So the reason why it looks different from the original one is that because all of this information about floating points and labels is actually not stored in the final executable, because labels are just, you know, numbers and stuff like that. All right, so that's pretty much everything we have so far, and yeah, let me go ahead and pour a cup of tea. How about that? What happened to the block cursor? I don't know. It happens from time to time. I can try to fix it. There we go, I just fixed it. I just made this window floating and then not floating again, and it fixed it. Welcome to i3 window manager, I suppose. Sometimes this shit happens. Yeah, I so got used to that, I don't even notice that. So, i3 by itself has so many different quirks, and I developed so many different reflexes to just either ignore these quirks or deal with them. I just don't even notice. Maybe it's also your expertise, who knows. So let's actually pour a cup of tea. Does it sound good? I think it sounds good. Just like me with GDB. Yeah, it's like basically open source. Welcome to open source, or maybe computers in general, right? Because everything in modern computers is fucking broken, and you have to just get used to that. No matter whether it's open source or not open source, it just doesn't matter. Everything is fucking broken. I would argue that these days Windows has way more quirks than Linux, to be fair. It's just way more quirks that you have to deal with on a daily basis. What kind of tea do you drink? Black, fruity, Earl Grey? I drink Earl Grey. That's right. Does GDP show register states? Yes, it does. GDP, you need to Control L all the time to refresh. Yeah, it's kind of annoying, especially if the program prints on the standard output. And you use TUI in GDB. It constantly breaks the TUI, and that never been fixed. So yeah, so dumb. Anyways, so what we're gonna work on today, we have a bunch of issues. I saw the pull request, I'm gonna address them later. So what we need is a function call return semantics. Right, function call return semantic. We already can sort of have function calls because you can jump to a particular labels, right? So in an example, all right, so we have labels, for example, loop, right? Here's a loop label, and then later you can jump to that loop, right? You can jump to that loop and basically repeat the instructions over and over again. So in a similar fashion, this is the conditional loop, by the way. You can also have an unconditional loop, which always jump there, right? So, and you can have some sort of a procedure, like, you know, sign, which does some calculations. And you can already just push some stuff onto the stack, right? And jump to there to sign, right? Jump to sign, and then handle, like, accept the arguments from the stack and do something with them. The problem is, once you're done computing sign, you have no way to return back to where you were, right? So there's literally no mechanism to do that. So you have, maybe you can do something like you need to know the current position of the instruction, right? You need to know the current position of the instruction, and you need to push the address of this call, address to this call to the stack, and then if you had some sort of an instruction that would take that address and use it as a jump target, you could probably return. And you know, in majority of the assemblies, such instruction exists, right? Such instruction exists, which basically takes the return address from the stack. In x86, if I remember correctly, such instruction is literally called return. So it's almost like a jump, right? In case of a jump, it takes the target as an operand. But in case of return, it's just a jump that takes the target from the stack. Thank you, TCMG69. Happy New Year to you too as well. Yeah, so this is how you wish Happy New Year in Russian, if you ever wondered. Without the last word, of course, and without the parenthesis in the end. All right. Cheers, by the way. Happy New Year. Oh, that's a pretty good Earl Grey. Thank you, Adnan. Happy New Year to you too. All right, so let's go ahead and maybe implement this instruction. So ret is literally GMP. Oh my god, 0x7001 subscribe tier 1, tier 2. Excuse me. Oh shit. Thank you so much for a tier 2 subscription, your first subscription, by the way. I hope you didn't misclick and that was intentional. Thank you so much, and welcome to our epic virtual machine assembly club. Cheers. The parenthesis at the end usually means smiley, but in short form. Trust me, we know. Anyway, so all right. So, and this is not enough. We also need some sort of an instruction that puts the current address, to the stack. But to be fair, do we even need that on the level of instruction? Because it could be done on the level of, let's say, assembly. But it actually reduces the capabilities of the machine. Okay, let's actually start with the instruction return, right? So we need to create a separate branch. So I'm gonna remove that. We don't need that. And So function call returns semantic. So the branch is 3. This is issue number 3. This is issue number 3, and let's go to the virtual machine. So hopefully adding a new instruction is super easy in our current code base. Where's GMP? So we have GMP, GMP if, and another instruction that we're going to introduce is going to be instruction return. So far we don't have that many instructions, I would say. It's actually kind of difficult to navigate. I don't know why. I think I didn't have enough tea yet. What the hell is going on with me? I think I'm an idiot. What the fuck am I struggling with? 21 instruction, yes. All right. Yeah, I'm getting old. I think I just need more tea. I think I just need more tea. All right. So where is the return? Okay, cool. Now, if I try to compile this entire thing, it will break in all over the place, telling me the places where I have to make the changes. Here they are. So this is basically a table that indicates whether an instruction needs to like accepts an operand or not. Right now we have instructions that accept 0 operands or 1 operand, right? So, and that's basically the table. So it's going to be instruction ret, and it doesn't accept any operand because it takes its data from the stack. That's kind of the point. So where's the another place? Okay, so this is the name for assembly. This is the assembly name. So this is going to be just return, and I'm going to just put it here, a return ret. So in assembly, it's going to be literally called ret. Cool. Any other places we need to make the changes? So this is the name in... I don't remember where we use this name. Do we even use this function anywhere? I don't quite remember. Okay. Yeah, we use it in one single place, I think, I presume. Wait, we never use it. We literally never use this function. What am I using it for? I think this is like straight up useless. If I go ahead and remove this entire stuff, I think nothing's gonna change. We literally don't need that function. We found a dead code. How about that? Maybe it was needed for some sort of like logging, but I don't think like at some point it was needed for something, but we actually removed that already. Okay, so now this is the execute instruction. So now we have to actually implement what's going to happen when that instruction is executed. So this is a very simple function. It accepts the current virtual machine, and when it encounters the instruction, it needs to modify the state of the virtual machine. So let's find instruction jump, because this is where we're going to keep all of our control instructions and except a jump if. So it's going to be inst ret. And what does it do? Right, what does it do? It expects one single operand. Okay. So if BM stack size is less than 1, right? If it's less than 1, then we have stack underflow, right? So that means we don't have enough stuff to actually jump anywhere. So, and the next step is going to be, we need to take the top of the stack. Top of the stack is going to be BM stack size -1. Here is the top of the stack. And we're going to assign this value. We're going to take it as U64, if I remember correctly. I think it has to be 64, because you can interpret stack frame in different ways. You can interpret it as unsigned integer, as signed integer, as floating point, or as a pointer, like an actual machine pointer. So yeah, in our case, the address is actually U64 because it's just the number of the instruction. And what we're going to do, we're going to assign it to IP, which is the instruction pointer, right? So we literally just jump in there. And since this instruction consumes the stack frame, right, it does consume a stack frame, we have to take the stack size and reduce it by 1. So this way we are actually like consuming the value on top of the stack. And there you go, the return instruction has been implemented successfully. And everything compiles pretty successfully as well. Quite successfully. Interesting, is it not? I think it's pretty interesting. All right. So now we can return if we have an address on the stack. But I guess, like again, this is not really enough. Thank you, Upper, so much for 16 months of tier 1 subscription. Thank you, thank you, thank you, and welcome back to Epic Virtual Machine Club. Yes, that's right. Welcome back. All right, so now I kind of tempted to implement a call instruction, but it feels like it's a little bit redundant. But maybe it is not. You know what, I'm gonna go ahead and implement call instruction, and then later I'm gonna do a revision of our instruction set and see how we can reduce it and improve it. But maybe some of the instruction don't need any improvement. Right, essentially, what do I mean by a call instruction? Right, so we have something like sign, which also returns from the function as well at some point. Right, so you're gonna be pushing some values onto the stack, and then you can do call scene. What this instruction will do, it will push the return address onto the stack and jump to this address. So then later you can use return. So how is your stack gonna look like? So you push a pi onto the stack, so it's gonna be 3, 14, 15, and then call will also push the return address. So let's call it this return address. So this is going to be your stack when you enter scene. So you will have to keep in mind that at the top of the stack you do have a return address and not the arguments. So what you will have to do, first thing, swap 1, and swap 1 will essentially just swap these two frames, and there you go, you have your argument here, which you can then do something with, right? And then you have to return the result, right? So then you will have to return the result, but at the same time you will have to return from the function. So you'll have to probably do swap 1 yet again to put the return at the top, and then when you return, it pops the return address, and here like at this point you have a stack with a result on top of it. So this is something that you'll have to constantly keep in mind. Right, so yeah, we're gonna use the same stack for both calls and for the arguments. And we don't have any registers, by the way. So that's kind of the special thing about this virtual machine. A single stack, no registers, no anything. Yeah. All right, so let's implement the call instruction, I suppose. Let's implement the call instruction. So before I implement the call instruction, I think I need to maybe commit everything. So first let me commit this thing where we returned this stuff, because apparently like I don't use this function anywhere. It feels like a completely separate commit. So this is when this is going to be 3. Remove dead code, right? And let me double check that everything, like, well, I mean, we recompiled everything, so there's no problem in here. 3, introduce ret instruction, and push that right into the repo. Cool. So I need to revert this kind of stuff. So let's go ahead and introduce the call instruction. Right. It does feel a little bit redundant, but again, I think I'm gonna actually. TCMG69 donated 6.
Я надеюсь, что ты сможешь получить хороший обед с этим.
Thank you for the donation and for a Russian message, but unfortunately I don't eat food. But thank you so much for $7. All right. How you recognize the amount of variables on stack for subroutine and the size of the variable? The size of the variables is always the same. First of all, the amount of variables on the stack. Well, you always know it. Did you know that when you make a function, right? Did you know that when you make a function f that accepts a, b, and c, you know that you accept exactly 3 arguments? Did you know that? I mean, it's right there. You can count them. 1, 2, 3. So the compiler kind of knows exactly the amount of arguments, and the implementer of the function also knows the amount of arguments. Like, yeah, does it make sense? Var args. Well, the question was not about var args. How does he differentiate different data types, though? Well, we tell him, I guess. Guys, all the information is known, like it's right there. Are you serious? Okay, so all of that information is known at the level of convention. When you make in a function, the amount of arguments and their types are the convention for that specific function. Does it make any sense? That convention in statically typed compiled languages is usually called signature. So when you make a signature for a function, you are actually encoding the convention for that function. You encoding that you're gonna have 3 arguments. The first argument is gonna be integer, the second one is gonna be float, the third one is gonna be char. You encoding that convention. On a lower level, it's impossible to encode that, but you can still imply it. You can still imply it, right? So in C, you don't have to imply it because you can be more strict about that. But Zozin, aren't you making a VM for dynamic language? Yes, true, but dynamic languages also run on x86 where things work exactly as I described. So how do dynamic languages work on x86 then? Good question. Anyways, does it make any sense? Does it make any sense? Magic. No, not really. So I see what you mean. I see what you mean. So essentially what I'm making is more of a cross-platform assembly at this point, I guess. So if you have like a dynamic language and at some point you're gonna compile it down to this virtual machine, you'll probably have to do dynamicness on the level of machine, and it should be pretty straightforward as we implement more and more features. Right now we don't really have that many features to do all of that, but soon it's gonna be more visible. You open me a new world of assembly. Are you saying that ironically or unironically? I'm not really sure. But to be fair, like assembly that we're using here on the streams is not real. So this particular assembly language you won't be able to use anywhere except in this project. So yeah. Not even a real assembly, yes. It's not even a real assembly, it's imaginary. Destroy computers. Oh my god. That was funny. Thank you so much for 20 months of a tier 1 subscription. Thank you, and welcome to our epic Tsotso club. Sounds horrible, but welcome anyway. So yeah, thank you so much. That's a really long support. Holy shit, almost 2 years, by the way. It's coming. It's fucking coming. Just like Billy Harrington. So yeah, we're implementing imaginary assembly, by the way. I'm unsure if you're familiar with this project, but we're literally implementing like virtual machine, but in the sense of like a JVM virtual machine, not in the sense of a QEMU or a VirtualBox, right? So, and we have our own assembly, and it's already Turing complete. Oh god damn it. We already have like example. Somebody submitted example that calculates number pi using our assembly and stuff. And our machine actually doesn't have any registers. It doesn't have any registers. It only has a single stack and not even a separate call stack. So the data stack and the call stack is the same thing and no registers. Guess how we achieved that? Guess how we achieved that? It's actually pretty interesting because it sounds kind of difficult to achieve that, but it's possible. We achieved that by introducing a swap instruction. So essentially, it allows you to swap any two frames, not any two frames, but two frames on the stack. So you have a top of the stack, right? And the rest of the things like A, B, and C, and we have address system that addresses the frames of the stack starting from the top. So the top's frame is 0, the next is 1, and so on and so forth. So it's relative to the top. And by doing something like swap 1, you're essentially swapping this thing with that one, and it becomes like this. So the top of the stack becomes an implicit register, right? So, and that's why we can have only one single stack, no registers, not separate call stack, nor anything, because with this swap operation, the top of the stack becomes implicit register. So it's kind of an interesting idea. And I'm kind of trying to play with it and see where it goes. And so far, it's possible to do pretty Turing complete-ish things with this thing. It's the problem is that you constantly have to keep track of a lot of stuff that is happening on the stack, but if you compile it down to this machine, maybe it's not that hard. We haven't implemented a higher level language that compiles to this machine yet, because the machine is not really finished yet. It lacks a bunch of features that are very important. So, all right. Cheers, by the way. Okay. So right now we're implementing a call return semantic. Debugger. Well, I mean, so are you guys talking about debugger? I mean, we do have debugger if I remember correctly. So you can do something like PyBM, right? So it executes and produces the pi number, as you can see. So this is the stack trace, and on the stack we have a single number, which is pi. And here are its different representations, because a frame can be viewed as unsigned integer, as signed integer, as floating point, or as a pointer. That will be needed for FFI in the future. So, and you can actually put a D flag, which allows you to step debug it. Right, on each step, you can actually, it prints you the next state of the stack. Maybe you should also print the current executing instruction and stuff like that. But yeah, it's gonna go for a while, by the way, because it needs to perform 750,000 of iteration to compute the pi number. But pi number is around here as far as I can see. So it's just jumping around inside of the stack and getting closer and closer to pi. So this is how it looks like. Why not implement implicit swap into call return? Because call is not implemented yet. Why are you suggesting me to do things for a non-existing code? What the hell is wrong with you people? Imagine arguing about non-existing code. What? Like every fucking time. I swear to God. We literally don't have that instruction yet. Okay. So, alright. Bike shading in a nutshell. So let's first implement something working that we can play with. Let's play with it, see its pros and cons, and make an evaluated decision based on the code that exists. That fucking exists. Okay? Alright. So let's implement the call instruction. Okay, so we have a bunch of places where we need to make the changes. So here it is, case inst call return. Does it accept an operand? Yes, it does accept an operand. It accepts the instruction address, of where it needs to jump, right? Okay, so I suppose the second thing we need to implement here is going to be this thing, inst call return, and it's literally going to be call, right? It's literally going to be call. And yeah, so the next thing we need to do here is to handle the call instruction. So case inst, I'm looking for return. Here is the return. Here is the return. So inst call, and what we need here. So we need to check that we are not going to overflow the stack, right? So if BM stack size is greater or equal to BM stack capacity, right? I think this is how it's called, BM stack capacity. This is straight up an error, and this is a stack overflow, right? This is a stack overflow, and there we go. So the next thing we need to do, we need to get the current instruction address, and the current instruction address is IP. Here it is. We need to push it on the stack. How are we going to do that? It's going to be BM stack, stack size, like so. There we go. We just pushed it on the stack, and we can increment the size of the stack. There we go. After that, we need to jump to the place located in an operand of the instruction. And by the way, this is not going to work. This is not going to work because stack is actually a union that you have to first interpret as a particular value. So in our case, I think we have to interpret it as U64, right? So, and after that, we need to change the IP to the instruction operand. How do we do that? I forgot. How do you get the operand? Oh yeah, so you take instruction operand as U64. There we go. So that's the whole call. So it pushes this thing onto the stack, right, and just jumps there. Alright, so that should be in the implementation. I think I forgot to... Yeah, I forgot to add a return and call to the assembly. So we need to take a look at the translate source code. So here is the translate source code. And I'm gonna add return. So it's gonna be return. Here it is. And after that, I need to add call, but call is going to be slightly, different because it also needs to be able to refer to labels, right? And if you're referring to labels in an assembly, you have to add yourself to the deferred operands, if that makes any sense. So essentially, I need to take BASM. So you can jump to the labels, right? Test. You have a label, and then you can jump to that label. Implementing something like that is super easy. You just go like with one pass, like remember all of the encountered labels, and then you replace those labels within the instructions. But what if you have something like this, right? You're trying to jump to a label that you never actually encountered yet while you're translating the source code. How do you do that? So you do that, like specifically we do that by deferring the resolution of the labels. So essentially when we encounter like jump ifs, or in our case soon we're going to encounter calls, and we see that they have labels, we put this instruction, the address of that instruction, to the deferred list. Then we continue translating and collecting all of the labels. Once we finish translating and we know the addresses of all of the labels, we go back to the list of our deferred labels and we resolve labels because we know all of the labels already. So, and that's why when we're implementing a call instruction, it has to be handled slightly differently right? It has to be handled just like jump or if. So essentially, if it contains a value, we're not going to add it to the deferred list. If it doesn't contain a value but rather a label, we add it to the deferred operand list that will be handled later after the translation. Make sense? Hopefully that makes sense. So eventually I think that has to be done for all of the instructions that accept operands, because why not allow everyone who accepts operands also like use labels as the operands? Why not? Doesn't sound like that of a bad idea. Also, it would be kind of cool to have like a label called $, similar to how BASM does that. Right. Similar to how BASM does that. Essentially, a $, refers to the current address. Yeah. Is everything okay? Why is chat Russian all of a sudden? Russian people, please. This is an English-speaking stream, right? Majority of people here don't speak Russian. They don't understand you. Nobody is understanding you here, including me. Please speak English. Like, I really don't want to start banning people for using Cyrillic. Like, I just don't want to do that because it doesn't look good. But like, people just don't give a shit. Like, I ask people nicely, let's speak English. All right. So let's continue. So jump if, and it's gonna be call, right? So this is gonna be call, and this one is also has to be call. Cool. It seems to be compiling. Nice. So what we have here, so this is the return, and did I push anything yet? I don't think I pushed anything. Yeah, I actually pushed everything. Okay, because I want this to be a separate commit as well. I want this to be a separate commit. Add a ret to BASM, right? All right, and wait a second. This has to be amend because I forgot to tag the issue. Wait, I forgot to tag the issue. Wait a fucking second. Did I include? Oh, for fuck's sake! I didn't mean to include everything. Now I have to git reset head. Actually, git reset. You see what happens when you start speaking Russian on the stream? That's what happens. I need more tea. I think that's what's needed here. Yeah, I just need more tea. Does anyone have any tea? Add ret to BASM, and then this is gonna be another one. Introduce call instruction. If you asked for English only when I send it message, it cuts out for a moment. My bad. Sorry. Don't worry about it. It's just like. The problem with Russians, I don't know how their brain works, even though I'm personally Russian, is that if one person starts to speak Russian, every Russian in the chat assumes that this is permission to speak Russian and this is a Russian speaking stream from now on, and everyone starts to speak Russian. Like, holy fuck. Like, what the fuck is wrong with you? No, this is an English speaking. That's why I just try to not encourage. I even try to not speak Russian. It's kind of difficult sometimes, but I'm trying to not even speak Russian on the stream because everyone. Oh, we can speak Russian now. So fuck all of that. Yeah, this is a Russian stream. Fuck that. Like, how does that even make any sense? Like, I'm Russian and I still don't understand that. So it's just really strange. Okay, so I think we introduced everything. So we have call and we have return. So another thing we need to do, we need to test all of that. We need to test all of that. So how are we going to test that? So I need to implement some sort of procedure that can do things over time, I suppose. I have a pretty interesting idea. Yes. The way we're going to do that, I'm going to implement lerp that basically interpolates values over some period of time, I suppose. Over some period of time. Okay, so kind nothing, please speak English. Nobody speaks Russian here, okay? So I'm going to implement lerp. So when this is going to be like this. So what do we expect here in the lerp? We're going to expect A, right, B, and T, right? So A, B, and T. And it's going to implement the usual lerp semantic where it's going to have A plus B minus A multiplied by T. There we go. So yeah, but I wonder how you're going to do all that, because lerps, so thank you for lerp meaning. Oh, by the way, this is another interesting thing. We usually define first all of the utility functions at the top, and then we have an entry point, right? Then we have an entry point. But in the current semantic of BM, we start executing at the zero, at the top. So it will start executing everything here. So we need to introduce some sort of entry point. So we can do something like main, which is going to be an entry point, and at the top of this file, we're going to do something like GMP main. You see? So basically, it will automatically skip all of these utility functions that we're going to have, and then jump straight into the entry point. So this is how we're going to do that. I'm not going to like make entry point customizable or anything like that. Entry point is going to be 0 always. If you want it to be in a different place, you can always jump there. I mean, come on. It's 2021. It's 2021. Just jump there. You see? Does it make sense? Does it make sense? I think it makes sense. To be fair, I also want to have this as a comment. You know what? I'm going to use a bash mode for maybe a sh mode. Yeah, there we go. That looks way better. I'm using shell mode in Emacs to actually distinguish between comments and everything else, because it's really not convenient. All right. So let's continue. How are we going to implement all of that? So essentially, you're going to be pushing A here, then pushing B and pushing T, and then you're going to be calling lerp, right? So when you're pushing things like that, on the stack is going to be like this, then on the top is going to be like this, and then on the top is going to be T, right? So we have to be a little bit careful about all of that. So, all right. And then when you call in all of these, of course, you're going to have a return address at the top, right? We're going to have a return address at the top. Yep. So the first thing I want to do, I want to duplicate the A, right? So 0, 1, 2, 3. That means I'm going to duplicate 3, and that will push A on top of here. So dupe is almost like swap, but instead of swapping, it makes a copy of that element, right, and pushes it at the top so we can operate with that element. Cool. Next, we need to evaluate this expression, right? We need to evaluate this expression. So that means we'll have to dupe 0, 1, 2, 3, 3 again, right? We need to dupe 3 again, and that will add B on top of the stack as well. So, and we need to subtract A from that B. So we could duplicate this A, right? We could duplicate this A, but we already have A here. We already have A here, so that means we can essentially duplicate 0, 1, 1. So and that creates another A here. So maybe first dupe could have been actually swap. It could have been actually swap. Maybe at some point we're gonna optimize that. So there we go. And after that, I can just do sub f, because the type here is actually floats, and for floats and integers we actually use different instructions, right? Because integers and floats and x86 and usually majority of the architectures have completely different formats, right? They have completely different formats. That's why we have separate instruction for floats and separate instruction for integers. You know, make sense? Hopefully makes sense. So call it lerp then. Good point. Good point. Thank you. Did I fuck up? Because I forgot how it works. I think I forgot how it works. Do we subtract top from the below one? Or is it below one from the top? Let me actually check out how it's implemented in BM, because I don't quite remember. I don't quite remember. So BM execute instruction, and when we are executing the instruction, so it's inst sub. Is it sub? Where is the inst sub? Is it minus? I called it minus. Why did I call it minus? Nice one. Inst minus f. All right. Okay, so we take the one that is below the top and subtracting the top. Okay, so that means I did everything correctly. So this is going to be minus f. Right, and that will subtract this thing, and on the top we're going to have b minus a. There we go. So after that, I need to multiply this value with t. Right, I need to multiply it with t. So, and to do that, I suppose I can duplicate 0, 1, 2, 3, duplicate 3 yet again, and get t at the top, right? So after that, I can mult f and multiply all of that, right? Multiply all of that. And again, by doing minus f, I'm subtracting this value from this thing. There we go. Isn't that cool? Isn't it cool? I think it's pretty good. Goddamn cool. But the problem here is that you also need to clean up the stack, because you're supposed to consume these values, right? You're supposed to consume them. Maybe I could have actually organized that slightly differently, but it is what it is. So 0, 1, 2, I need to do swap 2, so that swaps these two things, and then I need to drop it. So after I dropped it, looks okay. Okay, so I need to do another one. 0, 1, 2, swap 2, so that swaps these things like that, and I drop it yet again. Alright, so then 0, 1, 2, swap 2, and then I drop it yet again, and at the end I have a return address at the top, and I return from it, and the result is exactly what we wanted. So it's going to be clean up. So, yep. You could probably organize it a little bit better. So I think I should have not duplicate first A. I should have actually swapped it at the top. So then the cleanup phase would have been a little bit easier. But yeah, so that's the basically the specifics of working with our machine. The last minus. Yes, it has to be plus. Thank you so much. Cool. Alright, so looks cool. What we're gonna try to do here, I want to interpolate between 69 and 420, right? 420, and we're gonna put 0 here, right? We're gonna put 0 here, we're gonna call lerp, and we're gonna see that it equal to 69. Okay, so this is how we can test all of that. Since we have like function calls, we can now try this. So the result of the first call has to be 69. The result of the second call has to be 420, right? Because one pushes forward to 420. And then we can try something in between them. We can try something in between them, 0, 5, it should be something between 69 and 420. Lerp. Well, I mean, you're probably right, but look what's gonna happen. So I'm gonna just try to recompile everything, and then I'm gonna do BASM, input example, I think it just like this, lerp, BASM, and it's gonna be lerp BM, and the compiler actually told me that I'm using incorrect label. And this is because I'm not using some wimpy dynamic language that never tells me that before executing the program. Isn't that amazing? I think it's goddamn amazing. Alright, so yeah, let's actually quickly replace all these things. Unfortunately, this doesn't tell me the position yet, but we have a pull request for that I'm gonna actually look into a little bit later. Alright, so yep. We can try to go to the debugger and stuff, but maybe I'm gonna try to first try it for the first time. So let's actually figure out what is the first value. The first value is going to be 69, that's for sure. The second value is going to be 420, and we can try to calculate this value ourselves. Maybe I'm going to go somewhere here. Do you have lerp, by the way? Emacs doesn't even have a lerp. What a useless text editor, am I right? So what we're gonna do here is essentially then minus 69, 420, 69, and all of that has to be multiplied by 0.5, and the result is going to be something around this value. There we go. So this is essentially what we expect here from the virtual machine. And if we manage to implement that successfully, well, that's going to be a successful implementation of the call return semantic. And speaking of like automatic, like implicit swap in call, I don't think it's that useful, because you will still have to do a lot of different swap on the arguments anyway, and implicit swap is going to even more mess up your logic. So it would be better if call was just as simple and straightforward as possible. I even wanted to get rid of the call, to be fair. At the beginning, when I was actually like planning the design of this machine, I wanted an instruction that simply pushes the current address, the like current IP to the stack. That's what I wanted initially. And then later, like instead of doing call, you would do something like push current, or whatever the fuck is supposed to mean. I don't know, like maybe it could be something else. And then jump to lerp. Right, so it even reduces the amount of instructions and makes this push, like, you know, more explicit. And yeah, that's a good point, Beat69 stream, because I was actually about to transition that. Maybe we don't even need that instruction, and that instruction can be implemented on the level of assembly itself. Right, maybe assembly is going to have an implicit label for the current label, and there you go, you can do push and just jump there, and the whole call semantic is going to be only ret, which is basically jump, but the jump that takes its value from the stack. Push EIP. Why not push IP? The register that we have here, the only register in our virtual machine that we have is IP. Why not just push IP? Push it. But anyway, we don't even need a separate instruction for that. As I already mentioned, you could do something like that, right? But maybe it would not allow some interesting things. So first, we don't even know if this entire stuff works, right? So let's actually see if this idea works, and maybe then we can try to think about getting rid of the call and introducing an implicit label of some sort. Wait, would that not return to the push instruction? Oh yeah, it may return to the push instruction. That's right. Okay, so when we do... That's a good point. Thank you, thank you, thank you, thank you. So you actually caught a bug in our code as well. Because what we need to do here when we do a call, we actually have to push not IP but IP plus one. Yeah. Yeah, so it has to be $+1, and I just remember that in this. I forgot about that. That's a good one. Thank you. Trust Oracle. There we go. Don't get too cocky about that, otherwise you're gonna actually lose your trusted status. You know, some people make useful remarks, get trusted, and become too confident, and then get banned. So don't be one of those people. Thank you so much for the help. I had that problem with my assembly for class. Nice. It's actually pretty cool that you, like, in your uni or your school, I don't know where you go, you actually learn this kind of stuff. Because I went to a pretty shitty uni, and that's the reason why I'm doing it right now. Because my uni was shit, so I have to do it myself, essentially. Anyways, yep. So I think I need to recompile everything. And let's go. Let's go. All right, I think I need to, yeah, we need to test everything first, and then I want to make a cup of tea, chat. Then I want to make a cup of tea. So let me also add lerp to the examples. So it's going to be lerp bm, and it's automatically going to build everything there. So examples. Okay. It's did I call it lerp? Oh, it's lerp. Oh my god, literally blind. Okay, so it built everything. I also want to do the BASM just in case on the lerp bm, just to see if it did the right thing. Well, it's kind of difficult to see if it did the right thing, but so far, yeah. This is jumping to the main, right? We're jumping to the main. Then this is where the lerp starts, and this is where it ends because of the return. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, right? 15, this is where main starts, and we are actually jumping to 15. So here's the main pushing, like calling lerp 3 times and then calling it to 1. Everything looks good so far. Everything looks good so far, so that means we can try to do something like BME, and after executing the entire lerp, we should see 3 values on the stack. And here they are. The first value is 69, the second one 420, and the third one 244.5, and that's exactly the values that we predicted first tried implementation of the call return semantic. How about that? First fucking try, mate. That's pretty cool. That's pretty good and cool. So yeah, now if you program directly in BASM, right? If you program directly in BASM, you can split your code into separate procedures, right? You can decompose and you can build architectures and stuff like that. Isn't that cool? I think it's pretty cool. I think it's pretty goddamn cool. So yeah, but then I want to think about getting rid of the call. I think it's kind of redundant. So maybe by introducing something like just push +1, but actually introducing push +1, push $+1 means that I not only have to introduce like a special instruction, right, special instruction, but also arithmetic operations. So I could try to introduce a special label that has a name +1. So this is literally the name of the label, and it basically points at the next instruction. So yeah, and then in the future I can implement arithmetic operations for the assembler, Yeah, because it would be kind of nice to have like these arithmetic operations like plus I, all right, or maybe something like offset, and you would be able to like define offset somewhere here, you see? So, and then to have that and have it baked into the executable file. I think I'm paying too much attention to the assembly. This is supposed to be virtual machine for Lisp. Okay, so I don't know why I pay too much attention to all that. So is that a convention, by the way, double dollar? Is double dollar a convention? I'm not even sure if it's a convention, but could be. But before we go into that, I think I want to do a committee for everything, and maybe then even pushy. Okay. Hello, Cozy White Bear, and hello, hello everyone who just joined. By the way, really glad to see you all today. So I'm gonna commit the fix for the bug. Fix the bug in call instruction, right? And yeah, I watched your stream and I decided to become a software engineer, and now I work remotely partly thanks to you. You're welcome, I guess. I suppose, but I don't know, maybe. Because I left the industry, so you entered it. Well, congratulations, I suppose. You took my place in industry. That's what happened. I left the industry, and you took my place in it. That's right. I did it for you, specifically. Okay, introduce LERP example that utilizes the call ret semantics. Alright, so I forgot to bring a bowl where I'm gonna put all of my disposed tea leaves. So that means I have to go to the kitchen, and you know what that means. You know what that means, boys and girls. When I go to the kitchen, the things go wild. If you leave the stream while I'm in the kitchen, you're gonna be permabanned from this chat. That's right. So don't ban me. We'll see about that. Don't go anywhere. Don't go anywhere. Mods. Ban. Permaban. What's up? How's it going, everyone? Welcome back. Does anyone have any questions while I'm making a cup of tea? Certain increased demand in industry turning is technically making... I don't know how that works, but probably. Welcome back. A refresh, that means that, yeah, you're technical banned. That's it. You're done for. There go. Banned. Probably banned. Does anyone have any questions? While I'm making a cup of tea, of course. But why not push 1 followed by plus I1? Because push 1 already means a completely different thing. Not sure what you mean. Why you wear headphones on the neck and not your head? Because I have a really interesting anatomy. My neck is part of my head. So technically I'm wearing headphones on my head. Not 1 but $. So this is exactly what we were discussing. This is exactly what we were discussing Beat 69 stream. I don't know where we were, but we were discussing that like 5 minutes ago before I went to the kitchen. Does anyone have any other questions? Have you forgotten my nick yet? Also what TI... Oh, I remember your nickname. Yeah, I remember. Why did you start live streaming? Because I have no life. So, yeah. Does anyone have any other questions before I go to the kitchen again? How can I rewrite your Rust compiler in BASM? Easily. Okay, so I'm gonna go to the kitchen yet again because I need to turn on the kettle. Turn on the kettle. Don't go anywhere. Or, you know what's gonna happen. You know what's gonna happen. You know it. You know it. Ah! Everyone freeze! Hello. I'm back. Oh, wait. I think I finally understood what you mean. Byte 69 stream 420. I think I know what you mean. So instead of like introducing this shit where you could do like something like this, you could do something like push one add. Is that what you meant, right? First of all, this sum would be evaluated at translation time, while this thing will be evaluated at runtime. So you effectively will have one instruction versus three. And on top of that, it's not even about performance. It's about not forgetting to actually add these three instructions in this particular order, which increases the complexity and stuff like that. So it's kind of meh. It's just too much work. Generally. So also an address is a different type. It doesn't matter. It doesn't matter. So what we have on the stack, actually, where is the BM? Word? Yeah, there we go. So stack consists of words, and word is a union of these four types, and it just doesn't matter, right? So address is supposed to be U64, right? U64, and you add it, and yeah, you just add it as U64. There's no problem in here. Can I ask you why did you stop working in industry? Yes, you can ask that. Sure, go ahead and ask it. All right, so to be fair, I was thinking, I think having call is all right so far. Yeah, I think having call is all right so far. So I think I'm gonna leave the call. All right, so let's create a pull request, chat. Let's create a pull request. I didn't have to actually push that. So let's go ahead and do that. Why did you I'm sorry, you actually exceeded your limit of questions. Should have asked it right away. All right. Introduce call red semantics, and we're gonna actually close this entire stuff. It's PR time. That's right. You're goddamn right. So it wasn't really that much of a code, right? Plus 88, minus 32. Not that much of a code. But this is actually a pretty cool example. I really like it for some reason. I think we're going somewhere, chat. I think we're in fact going somewhere. All right. So we're just waiting until everything is built. And the next issue is going to be very, very interesting. Native function calls. Does it sound interesting? Native function calls. So what is that supposed to mean? What is that supposed to even mean? We're about to find out. So essentially, right now virtual machine is just like a pretty scuffed calculator, right? It's essentially a pretty scuffed calculator, but it needs sometimes to be able to do some things, some, you know, some useful things, for example, interact with an operating system. Right, and because of that, it needs to call to native C functions. We're not going to do DL open, by the way, Herberts and plots, right now at least. At least right now, we're not going to do DL open, but we're going to do something more simple. So we'll introduce a mechanism that will allow you to define a C function, right? To define a C function, and then sort of add this C function to your BASM environment. So not BASM, but BM environment, where you would be able to call that function. So that function is going to have a very specific signature, and that signature will accept the state of the virtual machine. And basically that native function is going to modify the state of the virtual machine and then go back into the BASM environment, BM environment. Why do I keep calling it that? Yeah, it's kind of, is going to be like that. So, and through that mechanism, we can introduce pretty cool things. For example, we can introduce a binding for malloc, right? So you would be able to allocate some memory with malloc in BM and have a pointer to the allocated memory on your stack. And then you're going to have separate operations like, you know, extract a character at that pointer, so you'll be able to do string operations and stuff like that. Right, so it's more of a like a bindings mechanism rather than native code. But you will have to load the code. Yes, we'll get into that a bit later. So you'll have to sort of like, we're gonna have some sort of a table with the native functions, right? It's gonna be a table with native functions, and before executing your virtual machine, you'll have to populate this table in the C code. So keep in mind that this is supposed to be a library virtual machine. A library virtual machine. So basically you would integrate it into your application, and you will have to prepare the virtual machine, right? And while you're preparing the virtual machine, you will populate that table of native functions and then let it go. But before we're gonna do that, my tea is ready. So I need to go to the kitchen yet again. And you know what that means? You know what that means, chat. You know what that means. All right. Kitchen stream when. I think I can actually like move my entire setup to kitchen and stream from kitchen literally. I have a table like a kitchen table, so I can actually put everything there. But it's probably not going to be that nice of a view. We'll see. We'll see about that. Okay, so did I fetch the latest changes, by the way? Did I fetch the latest changes? So let's actually go to here. Does it have small white tiles? I think it does, but I don't remember. I actually didn't notice, to be fair. Actually, cooking with sodium, I'm not really that good at cooking, and the food that I eat recently is not that even good anyway. So I'm on a pretty strict diet recently, so I'm not cooking anything particularly tasty. Alright, so yeah, I think I need to fetch the other stuff. Did I merge everything? I think I forgot to merge the pull request. Yeah, I forgot to merge the pull request. Alright, so let's quickly do that. Let's delete the branch. Me too. Everyone is on a diet. God damn. Sadge. T-Brew stream. I'll think about that. John does pretty interesting T-Brew streams, not gonna lie. Sometimes, not every time, but sometimes. Alright, so I need to create a separate branch for the native function calls. What's up, Lore Master? Welcome to the stream. How are you doing? So this is going to be the 5th branch. So the way it's going to work, let's actually go to the virtual machine emulator. So for example, let's imagine that I want to have a function that allocates the memory, right? So this function basically going to be like that. Let's call it BM alloc, right? So it's going to be BM alloc. What it's going to do, it's going to accept the pointer to the virtual machine, and that's it. It's not going to accept anything else, and it's going to return a possible error, right? If it succeeds, it will just return error okay. Okay, so essentially, how it's going to work. This function is going to work similarly to how a single instruction works. Similarly to how a single instruction works. If you have BM execute, what the hell is going on? Jiang, oh my god, Jiang, thank you so much. Ovu, thank you so much for 19 months of tier 1 subscription. Thank you, and welcome to our epic virtual machine club. Yes, that's right. Welcome. We're actually working on some sort of a FFI between your BM machine and C code. So finally, you will be able to do something useful with virtual machine. So right now I'm just trying to implement a function that will allocate the memory on the heap. All right. So from the virtual machine itself, from the assembly, you will be able to allocate some memory on a heap and maybe manipulate that memory and maybe call something like printf. Why not? We can also actually implement the bindings for printf. It's kind of interesting. So if you how is it gonna even work? Like, because you need to be able to put a format string, and it's kind of, we don't have mechanism for working with strings for virtual machines, so it's gonna be interesting. We'll see. All right. Hello, bad__1. Why are you reading? I guess ready for a little bit of a tea somewhere. I'm sorry. Okay, so this is how this function is going to be declared, right? And it's gonna work similarly to how a single instruction works here, right? So a native function is sort of like a custom instruction. That's what it is. So it will simply modify the virtual machine. But I think it won't modify the IP. I think IP is going to be modified for that function after the execution. Yeah, that's right. So, and okay, so this alloc will expect IP when I see people. What the fuck is this? Pong, out9 Pong. Okay, so BM stack size. All right, BM stack size, because we expect the amount of bytes to allocate on the stack. So this size of the stack has to be greater or equal than 1, but if it's less than 1, we'll have to return error stack underflow. Right, we have to return error stack underflow. So after that, what we'll have to do is essentially just allocate the memory. Just allocate the memory. So it's gonna be something like pointer. Oh, you know what? We can even do something like BM stack stack bm stack size -1 without even modifying anything, because this function is supposed to consume the frame and push another frame. We can just straight up replace the current frame like so by doing malloc this as u64. You see what I mean? You see what I mean? That's actually pretty cool. Right, we just take this frame and we take the value out of it, and then we replace it with the result of the malloc, and then we just return OK. So in malloc, if malloc fails, you will get the pointer equal to 0. So yeah, that's kind of cool. That's kind of cool. So this is the whole implementation. So, and this is a native function, a native BM function. So, and BM should have a list of those functions somewhere. The question is where. To have the list of those functions, we need to define the type of the pointer to the function. So it's going to be something like this. So type def. So this function returns error, right? And how is it going to be called? It's going to be called BM native func. Right, and the only thing it does, it accepts the pointer to the BM, right, and because of that, it has to be defined somewhere here below, and there you go. But at the same time, BM needs to refer to this function because we will need a list of these native functions, right? Native func, native funcs, BM native funcs capacity, and also we're gonna have like a native. So native func is too long of a name. It's too long of a name in my opinion. So maybe we should actually rename it to BM native, and it's just natives, BM natives capacity, and there we go. I think it's a little bit better. So, and then we're gonna have something like size would be better than capacity. Size is gonna be a separate thing because different instances of BM are gonna have different amount of the native functions. They're gonna be defined by the environment. Junk. Redirect politics. I don't know. That's okay. I understand the joke. It's a funny joke. Cheers, by the way. Oi, cheers. Okay, natives size. Native size. All right, that's actually very interesting. I kind of want to move halt somewhere here. And that becomes very interesting. Look, you have a stack, you have a program. IP is part of the program because it's an instruction address, so it's related to the program. And here is the native, so native functions that you can call from the BM. But again, here's the problem. BM refers, like native function refers to BM, and BM returns to native functions. So we have a infinite loop. Which means that I have to do something like this. Type def struct BM, and then BM like that. You see what I mean? You see what I mean? So welcome to C. Right, first I have this thing. Then, because of that, I can declare the type def for native without knowing the size of the native, and then I can refer to BM here. Infinite loops, and it will be our P. You guys are very funny. By the way, hello everyone who just recently joined. So this is going to be the new definition of the virtual machine, right? The new definition of the virtual machine, and I think we need to introduce a couple of interesting things. For example, BM push native, right? Push native, which accepts the virtual machine and a native function, and basically adds that native function to the virtual machine. All right, so let's quickly implement that. VM dump stack. Okay. And BM natives. BM natives size plus plus equal native. You're too slow. And also we need to make sure that this thing is less than BM natives capacity. There we go. So that's pretty cool. That's pretty cool. It doesn't even compile because I never actually defined that capacity. So far our capacities are, you know, 1 kilobyte. So I don't see, well, it's not really kilobyte, it depends on the size of the value. But so far I think it's kind of funny how all of these capacities are 1024. Why do we even have separate constants for that? Am I right? So yeah. Though maybe at some point I'll have to actually replace them with dynamic arrays, but I'm just too lazy to do that. Okay, everything seems to be compiling, and what am I building actually? I want to build like everything here. There we go. Cool. So, and the point here, when so this is BME, this is the emulator, right? This is the emulator. Here you load the program from file, right? You loaded the program from file. After that, we're gonna do push native. We're gonna provide the pointer to BM, and we're gonna push alloc. There we go. We're gonna push alloc. So now this native function is registered within the virtual machine, right? It is registered within the virtual machine. But the question is, how can we even call it? How can we even call it? We need a special instruction to call the native function. So what the instruction is going to be? Yeah, underflow. Thank you so much. Underflow. So I think this instruction doesn't matter what's the name. We can call this instruction native. It will accept an index of a native function within the array of native functions. Right, so you need to know that index up front. So basically the program that you're compiling is going to be very like environment dependent. It will expect a certain native functions at certain indices, right? Certain native functions at certain indices. So when you push alloc as first, doing native 0 is going to essentially result in calling alloc. And to allocate the memory, right, to allocate the memory, you will have to do the following thing. You will have to do push. I want to allocate, you know, for 20 bytes, right? I'm going to allocate for 20 bytes. I do native 0, and on the stack, I will get the pointer to the memory where for 20 bytes is allocated. Which is kind of interesting, which enables a lot of interesting vulnerabilities, because now your virtual machine will be able to do buffer overflow. So, and by the way, at some point, your virtual machine will be able to locate the machine itself in the memory and try to modify the behavior of it. So it's actually kind of dangerous. So it's gonna be interesting. Have you worked on the architecture of this virtual machine beforehand, or just doing this on the fly? I'm doing it pretty much on the fly, I suppose. Sometimes I think about it when I'm in a toilet or in a shower. So does that count as the, you know, working on an architecture beforehand, if I'm doing that on the toilet or in a shower? I don't know, it depends. So it depends on the definition. Okay, so yeah, that's gonna be the idea here. So, and we need to introduce this instruction, right? The native instruction. Sodin OpenAI researcher. Yeah. Actually, holy shit. This sounds as a like a interesting CTF problem. You have a virtual machine that has a native interface that returns the real pointers to the real memory. So your task is to actually like manipulate the heap get it to the particular state, get a particular pointer, and locate something within the memory of the virtual machine of the interpreter itself and modify something there from within the virtual machine, basically escaping it. Sounds interesting. Oh, you did this before. It was a pain to reverse engineer the VM. Wait a second, did you participate in one of these CTFs or something? That actually sounds interesting. Cool. You're an actual hacker, what the fuck? So, by the way, one of the ideas that I had is that after we're done with... Oh shit, we have a raid from ToggleBeat. Thank you so much for the raid. We're developing a virtual machine. So, what I wanted to say, after we're done with the advent of code, I was actually considering to start doing some CTF archives of some sort. So yeah, maybe at some point we can try to do something like that. That's actually pretty cool. Hello raiders, we're doing pretty epic shit right now. So we're developing a virtual machine, but a virtual machine in a sense of like a language virtual machine, JVM, not the VirtualBox or QEMU. Let me show you what I mean. Is this stuff even compilable right now? I think it's compilable. So it consists of actually 3 executables. Let me show them. So first you have BASM, which takes an assembly of our non-existing virtual machine, right? An assembly usually looks like this, right? So here's the assembly, right? So this is a program in assembly for our virtual machine that calculates number pi. Right, it calculates number pi. Then you can use this BASM to convert it to our machine bytecode, like this. So it's going to be pi BASM pi BM. So, and what you get is pi BM, which is a data file, binary data file. You can take a look at it at hex dump. Right. So this is the bytecode for our virtual machine. Right. It's pretty cool. Then you can emulate it. So we have a special emulator that accepts the bytecode pi BM and just executes it, and it spits out the pi on the stack. So basically we don't really have like input output implemented for the virtual machine. So right now, to get the result from the virtual machine, we just dump the stack of the virtual machine. It's stack based. It doesn't have a single register, and it doesn't have a separate stack for function calls. It's actually very interesting. It only has a single stack, both for calls, for data, and not a single register. And it's Turing complete, by the way. It's Turing complete. So, and another thing that we have here is dBASM, which allows you to take any bytecode file and disassemble it and inspect it and look at it and stuff like that. I love how the bytecode is mostly null bytes. I mean, yes, this is because the size of the instruction is fixed, right, and it consists of 2 64 numbers. Well, we can probably change that later in the future. So the virtual machine is not stabilized yet. So let's take a look at the instruction itself. Yeah, so it literally consists of an instruction type, which is a noun, so it doesn't really mean that it's 64. It could be 32 bits. And the word, which is exactly 64. I think it's like 32-bit number and 64 bits or something like that. So yeah. And today we implemented function like call return semantic. So now you can actually define like separate procedures, right? For example, we defined the function lerp, which is linear interpolation, and you can implement it like that. And then in your main program, you can call this lerp and it will work. How about that? Isn't it amazing? So now what we're working on native function calls. Essentially, you will be able to create a function in C and then bind it to the virtual machine environment and call it from the virtual machine assembly. So that's what we're working on right now. And yeah, that's pretty much what we're doing. Does it sound interesting? You can find the source code of the thing that we're working on here. It's completely open source. It's under MIT license. That means you can do whatever you want with it, even sell it, without even telling me about that, and make a lot of money. How about that? Sounds cool? Sounds cool? Just grab the source code and sell it on the internet and make a lot of money. And you have my permission to do that. All right. So, but keep in mind that anyone else can do the same. So it's probably not going to work. So that's kind of the point of the open source. So yeah, we basically attached a lock to our virtual machine environment. The BM makefile is already GNU make dependent. Well, how is it GNU make dependent? Is it because of this? Is that a GNU thing? Wait, really? Is that a GNU thing? God damn. But it's so convenient. Why is it not a standard yet? I don't know, like so far, like GNU make sounds better than BSD make because it has all of these useful things. Like, come on. Why is this not part of the BSD? Like, it's so convenient. Can we embed it in biological neurons for the true Android experience? Well, you have my permission to do that in license. You can do whatever you want with it if you want to. Sure, go ahead and do that. BSD has other convenient features. The one I can think of probably jails, but I never tried them myself, so I don't know how convenient they are. All right, so yeah, so to make a native call, as I already mentioned, we will need a separate instruction, right? So how do we implement native calls? So in the virtual machine definition itself, right, we're gonna have a list of native functions that you can call, and we're gonna have a separate instruction that accepts an index of that native function and then just calls that native function and then returns back. So that's going to be the idea essentially. So when you define a virtual machine, you're going to have a stack, you're going to have a program which stores the instructions that you implemented, and then you're going to have like a native functions. All right. So let's go ahead and introduce a new instruction. Are you guys ready? Are you guys ready to introduce a new instruction? There we go. So does anyone have any good names for that instruction that makes a native function call? I'm thinking of just calling it native. I think it makes sense. I think it's a pretty good name for a native function call. Can't come up with anything better. So I'm not really creative when it comes to this kind of stuff. Will we write a LLVM backend for it? Probably not. I'm definitely planning to have a JIT for this machine, right? So essentially there will be a special function to translate BM bytecode into, for example, x86 or ARM or RISC-V. But I want to try to do that myself without LLVM first and see how it goes. I'm pretty sure it's going to be a huge pain in the ass and I'm going to regret that, but at least I'm going to try that. Inst native. It returns a single argument, so it accepts a single argument, so we're going to put it here. All right, so boom. So here's the call, and the name of that instruction is going to be what? What is going to be just native? This is how we're going to call it from the assembly. How did I put a here? All right. So, and now we need to implement the interpreter for the native call. That's what we need to do. It's going to be inst native. There we go. There we go. Cool. So the index of a native function is located in the instruction operand. So this is where it's located. Here it is. It's in an instruction operand. But if the instruction operand is greater than BM native actually not capacity, but rather BM native size, right? That means you're trying to refer to a non-existing native function, right? So that is supposed to generate an error, but we don't have an error for this kind of situation, or do we? That's actually a pretty good question. Do we have something? So illegal instruction, so we have a legal operand, I think. Yeah, I think it's a good one. A legal operand, because you have a native and you're passing an illegal native function index. It's straight up illegal operand. So I think we can use this thing. Oh, that's bad. Inst native. Yeah. So there we go. Illegal operand. Cool. Next thing. We take BM natives. And we take the index from the operand, right? And then we just call this function, right? But we call it with BM, which is kind of interesting. So, is it undefined behavior? I don't think it's undefined behavior. I think it should be okay. All right. And after that, we should increment the IP, right? So we take a native function, we call it according to the operand, and then we increment the instruction pointer and continue execution. So there we go, we have a native function. How about it? We have a native function. I think it's pretty cool. Okay, let's try to compile all that, and it seems to be compiling. And I'm gonna try to compile all of the examples. I'm trying to compile all the examples. All of the examples also compile quite well. I think I forgot a very important thing. I forgot to add native to the to the assembly. That's what I forgot. Return, print, debug. So we'll probably also, after we have native functions, we'll have to get rid of the print debug. Because now, for print debug, you can have a native function. And this is something we have to implement, actually. I think this is something we definitely need to implement. Okay, so I need to add a native. So this is not going to be swap, but it's rather going to be just a native. Do you want to store the memory pointer on the VM stack? Memory pointer on the VM? Yeah, this is going to be the idea. Because you're going to have other native functions that accepts those pointers. You see what I mean? So for example, if you have a pointer to a string in the memory and you have a function that prints that string, you basically, what you're doing, you're taking a pointer on the VM stack and you're pushing it to another function. So your machine becomes like a glue code between these native functions. Make sense? How you print all the buffers in VM? You just print them, I suppose. You can also ask Google, I think. All right. So let's actually try to see if we can allocate some memory. Are you making something like in JVM? I think so. I think you can say it like that. Yes, I think it's kind of a JVM, but it's not JVM. At least it's not slow as JVM. All right, and it doesn't have any garbage collector. Does JVM have a garbage collector on the level of JVM? I think it does. All right, so let's do alloc BASM. Right, 3 billion devices. That's a good question. Okay, so we're gonna have main function and shmod, right? So halt. So we're halting the machine, and then we're gonna do something like jump main. So this is like basically a boilerplate for the BASM, right? So you define an entry point, you jump to that entry point, and within it you end it with halt. Makes sense. Okay, so let's try to do the following thing. I'm going to push for 20 on the stack, and then I'm going to do native 0, right? And that is supposed to allocate some memory there, right? It will allocate some memory and push the pointer to that memory on the stack, and we can try to observe that memory. So let's go ahead and do that. So let's see if it's going to compile. So I want to add. So, you know, keeping the list of these examples like that is really inconvenient, right? Can we do something like shell ls? You know what I mean? Because I think makefiles do have that. It's going to be examples, shell ls, examples, right? And then sort of replace replace their specifically what we're looking for. We're looking for BASM files, right? Specifically, we're looking for them, but I think after that you can also replace some stuff. Let me Google it up. It's actually very interesting. It's gonna be GNU make shell replace extension. Shell find example BASM. We can do that. Modifying file extension, but that's not the point. What I need to do here is to modify their okay, for file do this is to there was a simple. Okay, here we go. You can do wildcard. Yes, it's actually wildcard like this. So we define a wildcard with a particular extension, and then you can wrap that wildcard with that thing, replacing one extension with another. Right, so the first extension is going to be BASM, but you replace it with BM, and this becomes your your examples. See what I mean? So now what this is going to do, it's going to try to build any BASM file within the example folder. We did F a little bit, we dropped a couple of frames. Right, first you do a wildcard, and then you replace BASM with BM. And it's kind of convenient because we don't need BASM files, we need specifically BM files, and that requires some, you know, string processing. Alright, so that's pretty cool. And if I try to build examples now, it actually builds all of them. And does it build a log? Yeah, it did build a log. So whatever I put into examples, right, whatever I put into examples, for example, hello BASM, which is an empty file, right, and I try to build examples, it does build it automatically. I don't have to add it to the make file. So essentially it just searches for all of the BASM files, and it always builds them and puts them into back into the example folder. This is actually kind of cool, I think. Alright, so hello, and I'm gonna just remove all of that. Yeah, GNU make is too convenient. It's just too fucking convenient, which is kind of ironic, you know? Which is kind of ironic because, you know, Richard Matthew Stallman always goes around and talks about like convenience versus freedom, and how you always choose freedom because the convenience is the like evil capitalistic tool of making you a slave, while GNU and FSF doing exactly fucking that. They're using convenience to actually make software dependent on their stuff. Like, holy fucking shit. Can you be more hypocritical than that? But of course, it's okay because they are not fucking evil. Holy shit, like... oh, it's just so fucking frustrating. They literally became the very thing they swore to destroy. Like, not gonna lie. But that's okay because they're good guys, right? Anyways. So this seems to be working. Don't worry, they're the good guys, exactly. It has serious bugs in the parallel build features and dependency resolution. But yeah, but how does that contradict with the convenience? Okay, so what I was doing, I was trying to take a look at this thing. The BASM example alloc BM. Cool. So this is the disassembly, and disassembly works quite well. It looks kind of funny how like jump one, and you just jump to the next instruction. So yeah, but the reason why we have jump one here is because we have an entry point, and at any point I can add more functions here, right? And that entry point can be shifted in the future, so that's why I have that jump here. Which maybe, I don't know, we probably need some sort of optimizers, right? That essentially, if they encounter this like something like jump one, they can probably get rid of that. Yeah, ASM optimizer, like, or at least BM optimizer could be an interesting thing to work on. BASM mode when you implement it. We can actually work on that probably at some point. Do we have an issue for that? BASM mode. Let's create an issue. Sometimes I actually, like, the thing is, sometimes I hold myself back from adding in issues because I feel like somebody's gonna take it and implement it not in the way I wanted to implement it, and they will submit a pull request. And of course, I can just assign it to myself, but quite often people just don't look at who assigned there. So that's why I don't like to create this kind of issues, because somebody is gonna try to take this issue without even asking me, right? They will implement it in completely different way, not in the way I want it, and they will submit a pull request and say, look, I did it for you, and what do I say? Well, you did it not in the way I wanted it to do, and what do I do with it now? So yeah, I'll think about it. It's open source is hard. Open source is hard. All right. I wish people would ask before taking issues. That would be actually kind of cool, but nobody asks before taking issues. All right, so let's actually do BME. BME, and let's take a look at the final result. So I'm gonna do that D, and first we push. Oh yeah, we did a jump first. We definitely need a way to actually observe the executed instruction. Isn't the point of review to tell people they didn't do it properly? But I mean, if it's completely not in the way you want it, so what do you say? Do you go through the whole thing, wasting your like day explaining in detail why it is not the way you want it? Why would I spend my time on that? But if I say you didn't implement it not in the way I want it and close the issue, just look like an asshole. So you have two like choices. You waste your day explaining in details why it is not the way you want it, and maybe participate for another day in some sort of bike shading flaming, or just close it without explaining, saying I don't like it, and look like a complete asshole. Which one do you like? Tell me, which one do you like? So I don't know. Maybe I just need to accept that people will view me as an asshole. I think, yeah, I guess the second one. The Linus Torvalds way. Yeah, probably. Do both. Yeah. Holy shit, what the fuck is this? What is it? Is that gonna steal all of my data if I open it? I opened it, by the way. That's really interesting. It's a really complicated way of doing that, to be fair. But I see what you mean. Oh, we have a raid from Donho. Thank you so much for the raid. And raiders, welcome to the fucking stream, mate. Hello, hello. Okay, I think I want to expand my my emulator. Expand my emulator and also print the instruction, the current instruction that we are executing. I think that's gonna be useful. That sweater looks comfortable. Thank you. I actually really like the sweater. It looks really cool. So what we're gonna do, I need to take the current instruction. So the current instruction is located in the program, not provided, program BM IP, right? So here's the current instruction. So, and I forgot the definition of the instruction, something like inst. It's not really inst type, but yeah. So type, and then you can do something like inst type as inst type name. Yeah, inst type name. Inst name. So I can easily convert the type of this thing into a name, which is kind of cool. So, all right, I'm gonna put it like this. Get char. It's gonna be printf s, then not really LLD. You have to use this PRI64. Yeah, you have to use this thing, I think, for cross-platform printing of 64-bit numbers, you know, the fucking classic. And then it's gonna be a new line. Yeah, because on different platforms like Linux, Windows, and Mac OS, the 64-bit numbers are just like type-deft differently, right? I think on Windows and Mac OS they're long, on Linux they're long, and because of that, like Jiang actually explained that really well. Because of that, you may have warnings because you're using not really like correct format strings or something like that. It's just fucking insane. Welcome to C, I suppose. Welcome to C. Then we have an operand, and I'm gonna always print an operand as U64. It's extremely ugly, but actually Kolombetka went through the effort of replacing all of these LLDs with PRI U64 or I64, so yeah, that should be okay. Alrighty, so yeah, we're gonna actually print that instruction. Okay, it doesn't even work properly, BM, because this BM is not a pointer. Yeah, we have to do it like that. Why support other platforms? That's a good question. Ask that question to Hudson Plot. Because he has to always suffer when he tries to build any of my projects, and I feel bad for him. I'm really sorry, Hudson Plots, but GNU Make is just too convenient. I'm really sorry, it's just too convenient. What can I say? The vendor locked me. That's it. They vendor locked me. All right. So okay, now if I try to do that, here is the instruction that we're trying to execute, and yeah. So after this instruction, we're gonna have 420, and now we're gonna perform a native call to 0. Let's see what's gonna happen. So we have 420 on the stack, and we're about to perform a call. And congratulations, we just leaked a little bit of memory. Because we're allocating the memory, but we're never cleaning it up. So yeah, I guess. And then we can halt, and that exits, and now we have leaked memory. Can we confirm that with valgrind, like this? Okay. All right, so we're jumping, pushing, calling, halting, and there we go. Still reachable, 420 bytes. We literally leaked 420 bytes as expected, which is kind of interesting. So we leaked exactly expected amount of memory. Amazing, absolutely amazing. All right, so maybe we need to introduce like something like free or some, yeah. So BM lock. So we may introduce something as BM free. Right, and what it does a very similar thing, right? It does a very similar thing where, you know, it expects a value on the stack, and it just takes that value on the top of the stack and interprets it as a pointer. So you see this as PTR is primarily used by the native functions. And then you just free this entire stuff, right? And after that, you should not forget to decrease the size of your stack, because free is supposed to consume that value, and then you return error or keg. There we go. Cool. Error or keg. So now in a log BASM, you will be able to do something like native 1, because as you push another native function, it will have ID equal to 1. We might as well actually make push native return the index of the of this function, but yeah. Yeah, so this is going to be free, and in a log you do native1. We also need to recompile everything. We also need to recompile, and then recompile all of the examples, and then we can try to execute that. Okay, so we're pushing for 20, so we have for 20 on our stack. We're allocating some memory, so here's the pointer in the allocated memory, right? And I forgot to yeah, so after that we freed that memory. As you can see, we used that pointer, we freed that memory, and now the stack is empty. And now we're halting the machine, and as you can see, all heap blocks were freed. So we allocated a little bit of memory and then we freed it, and this is the mechanism for interacting with native functions, which is kind of cool, isn't it? I think it's kind of cool, in my opinion. So the thing we can do now, I think we need to commit whatever we have. So yeah, first I want to commit yeah, I think it's gonna look a little bit better. So if I try to now execute the debugger now, right? So it has that, it just points at the instruction. Maybe we need to explain instruction like this. Maybe it's gonna be a little bit better if you do it this way, right? Yep. So stack instruction. So here's the currently executed instruction, then push. Yeah, cool. That's actually pretty cool. All right, so I want to commit that, and this is going to be print currently executing instruction in debug mode of BME, something like that. All right, and the next thing is going to be introducing the native call mechanism. I think everything here is a native call mechanism. Introduce native function call mechanism. There we go. So add alloc and free native functions to BME environment. So now when you're executing your program in BME, you can allocate memory, dynamic memory, and deallocate dynamic memory. So you still have to deal with that memory yourself. And I'm still thinking, do I need any garbage collector? Because yeah, maybe it's going to be a very useful thing to have that garbage collector. Basically, you allocate and you never have to free, and then the garbage collector is going to analyze whether you ever use the allocated memory somewhere, and if it's not reachable, it's going to automatically free it. We can try to work on that. All right. So another thing I want to commit here is automatically build every BASM file in examples folder. There we go. Okay. 5 add alloc BASM example. All right. Technically, we implemented native call mechanism. Technically, we did it. So, and to be fair, because now we have a native call integration, we don't need such instruction as print debug. The point of this instruction is to essentially just print the frame for testing purposes. We don't need that anymore because we can literally implement it as a native function. So let's go ahead and remove this instruction completely from the virtual machine and introduce a couple of native functions that can print the frame as signed integer, as unsigned integer, as floating point, or as a pointer. And yeah, so your environment may not even have these native functions. If you think about it, native functions are an extension to the instruction set of the virtual machine. That's what it is. That's actually very interesting, because each native function, look at that. So this is how a single instruction looks like. This is like a single instruction. And if you take a look at BME and, for example, alloc, the handling of this instruction looks kind of similar. Like, you can technically move all of these instructions to native functions and have only one instruction called native. So yeah, native instruction call is essentially just an extension to the instructions of the virtual machine. Isn't that interesting? So yeah. So we basically can add more and more instructions. I think it's actually pretty cool. There's like something philosophical about that. So we can even have a virtual machine with a single instruction native. Which is kind of dumb, but you can do that. Like, okay, but it's gonna be like, it's gonna be a different virtual machine depending on the environment and set of native functions. So I don't think it's that useful. I don't think it's that useful, but it's kind of interesting. I'm gonna lie. All right, you see what I mean? See what I mean? Okay. Yeah, native 0, native 5. Yeah, this is exactly how it would look like if we just remove all of the instructions but leave natives, right? Oh, and speaking of DL open and DL stuff, we can try to tackle the idea of actually like dynamically loading these native functions. Yeah, you can have these instructions like native functions in DL, and they have to still have this this signature, but then you can actually load them at runtime without having BME recompiled. Then you can just have define plus native 4. It's kind of interesting, but I think it's not that useful for JIT. Right, here's the problem. By moving all of these instructions to native functions, you lose information about those those functions and what they exactly do. And if you have a JIT compiler, it have no idea how to compile those native instructions, right? So when we're going to implement the JIT compiler, it's definitely not going to try to optimize and do something with the native functions because it has no idea what native functions do. And the only reason why we have these things as not native functions is because we know exactly what they do. They standardized, so JIT can use their semantic to modify the program and optimize it and then translate it to native code. See what I mean? So yeah, everything that has to be optimized and processed by the JIT has to be a proper instruction and not a native function. I think that's kind of the point of this. What is this stuff? Is that a fucking ad in my chat? You could code also stream rent a coder. Okay, so now you're getting a timeout, I suppose. List 35. 1 hour. I think 1 hour is gonna be okay for you. Invalid you? Oh, it's because it's H. I'm sorry. 1 hour timeout. All right. So what else do we have here? Okay, good. Mods? Perman. Alright, what else do we have here? Yeah, I wanted to remove print debug. I wanted to remove print debug. Let's see if we can now compile all that. So we don't have a print debug anymore. Fuck that. We don't need that. And now we don't even need that. So this entire stuff goes away. Cool. And after that, I think I need to try to build the examples. Cool, they still build. This is amazing. Remove print debug instruction. And let's push that right into the repo. Let's push that right into the repo. Now, how can we implement all of these like special instructions and shit? Is going to be BME. Let's go ahead and implement something like BM print float, maybe print F64, right? So this is a thing that is going to take the first stack, the top frame on the stack, and print it as a float, nothing special. Hello, what I did passing by, welcome to the stream. If BM stack is less than 1, then error stack underflow. That's right. And what we do here, we just do print F, LF, maybe even LLF, no, just LF. BM stack size -1 as F64, right, as F64. And then we have to reduce the size of the stack size -1, and then just return error oak. ebisp. Do we need to command ebisp? All right, so let me edit. Add cmd ebisp. https github.com zozin ebisp. Yes, that's how lazy I am to switch to the browser. Yes. Cool. So we have print F64. Print F64. Now I should be able to do BM push native BM print F64. There we go. That's it. So now you can do that stuff. Isn't that cool? Isn't that cool? So you also have to keep in mind that this is 0, this is 1, and this is 2. So, and we need a better mechanism in BASM specifically, to refer to these native functions. Maybe. So how can we even do that? Let me see. So specifically in the P BASM, I want to do something like extern print F64 2. So this is what I want to be able to do. Right, and here we're gonna have alloc 0 and free 1. So then later you can refer to these things in native print F64, right? And it will resolve accordingly, right? It will resolve accordingly. To be fair, it would be even cooler if we supported like DL open, right? DL open, and then I could do something like this: F64 and free and alloc. So the idea is essentially you have DLL with all of these native functions. You run BME and you supply the DLL. BME DL opens that DLL, and DLL should have a function get function pointer by name, right? Get function pointer by name, and then it will query the function pointer by this name and populate the function table with them, so you don't even have to worry about that. But that means the name has to be part of the binary file, so it's going to be kind of complicated. We'll need to think about that. So for now, it's going to be just this. But I think in the future, we can actually make it super convenient. I think it's going to be so super convenient where you could have like these native functions in DLLs and you can supply them at runtime. I will need to think about that mechanism. And I also need to think whether we even need that mechanism, because it starts to sound like something out of the scope of the project. All right, so yeah, let me go to BME. So we're gonna put it to do here. We're gonna put it to do, and some sort of mechanism, to load native functions from DLLs. I know that DLL is a Windows term, but I kind of like it better than SO. You know why? Because if you're a Windows user, right, and you hear a term shared object, you will have no idea what the fuck a person is talking about. Whereas if you're a Linux user and you hear the term DLL, you don't like it, but you still know what the hell people are talking about. So that's why I like DLL better, because even though it's like a Windows specific thing, when you said DLL, everyone, no matter what is their main operating system is, understand what the hell you're talking about. You see what I mean? It's like a more known term. So is normie pandering. Like, I mean, you have to communicate with normies at some point, right? So this is what it is. And not everyone who uses Windows is a normie, by the way. Same argument can be used to call super key the Windows key. Yes, so what? It's me, I'm a normie. No, I'm a normie. Okay, so what I wanted to do? Oh yeah, I was in the middle of implementing the print function, right? So for now we're not gonna have that. So I'm gonna actually put it to do here. To do. It will make it a body, so I think this is what we have to do here. To do extern declarations for BASM files. Extern native functions declarations for BASM files, and here are the examples. So what's interesting is that this is a very important thing in Snitch. For those who doesn't know, Snitch is a special tool that locates to-dos in my source code and your source code, like any source code, and reports them as GitHub issues. And basically, if you define something like this entire thing will be interpreted as a single to-do. Right, so this will become the title of the issue, and this will become the body of the issue. To prevent like Snitch from making this a body of the issues, you put like a body breaker, right? So then once Snitch encounters something like this, it will stop parsing and it will consider only this thing to do. So it's actually a pretty useful feature. So yep, that's why I put this thing here to separate it. All right, what I wanted to do here is now we clean the stack. We clean the stack, and after that we want to do a native too, so that will print the value on the standard output, right? Something like print the value. Yep. So now the program that computes a pi will not only compute the pi, but also automatically print it on the standard output, and that's going to be the actual like intended behavior of the virtual machine. And because of that, I think we will be able to get rid of the dumping the stack in BME at the end of the execution. So at the end of the execution of the emulator, we dump the stack because we don't have no other way to print the result of the execution. Now with native functions, we do have it, so we can get rid of that behavior, which is kind of cool. Yeah, this is literally broke. Yeah, by the way, it was not implemented by me, so it was implemented by Dear Pandas, I think. Let's actually blame this file. Thank you so much, by the way, for implementing that. It's actually super cool. Show committed in lines. Dear Pandas, yeah, if you're watching right now, thank you so much for implementing this. This is such a useful example. I keep using it for testing different things. So yeah. So, and it actually computes the pi number, like it performs this amount of iterations, and Okay, so here we clean up the stack and then we are printing the value, and let's see if it's gonna work correctly. Yep, let me recompile that. Let me actually recompile first of all everything. Comparison. Yeah, that's a good one. Stack size is less than 1, that means we have an underflow. I gave up understanding your ninja coding skills a long time ago, but it's very entertaining to listen to regardless. I'm not even doing anything special. What are you talking about? Okay. So we're ready to try to do that. So it's going to be BME example. Hello, Flame Kasai. Welcome to the stream. And I think I have to do something like BM. There we go. It printed this thing. And then we still have a behavior where BME prints the stack. So this is something that we need to get rid of. All right, so let me try to do that. I'm going to go to the BME. We're already in BME. So, and that's exactly what we do here. Yeah. Do we really need to get rid of that? I think yes, because we still print the stack when we are in debug mode, right? So you can do something like D, and you will always see the stack before executing. Yeah, I think that's useful. Yeah, that's cool. So we can completely get rid of the dumping the stack. So before, let's print everything. Maybe dump on non-empty. No, we don't need that because we already print the stack in debug mode, right? So basically, if you're running the program in a non-debug mode, there is no any reason to put any to print any debug information. Let's print all of the debug information in the debug mode. So I think it makes more sense. And examples, right? And let's just try to execute this entire thing. Not in a debug mode. And there you go, here it is. How about that? Isn't that amazing? I think it's actually kind of cool. So yeah, we're just executing this thing and it just prints the pie as intended. It's actually kind of cool. It can probably print the pie like on each iteration, but I'm not sure how useful that is. All right, so here's the BME. It's a pie. And we can do the same, for example, for E. So we have an example that computes E that I implemented this time with the help of a chat. And yeah, we can try to do the same thing for it as well. So it's going to be BME. Boom, and right now, as you can see, it doesn't print anything because we got rid of the stack dumping behavior. But what we can do now, we can just do native 2, and that will print the floating point thingy as well. Yeah, I need to recompile actually everything. I think I need a way to recompile like always everything. And there we go, so it also prints number E. It's pretty cool. All right. So I'm gonna make a separate commit here. Don't print. Let's actually put it like this. Make BME to not dump this stack in a non-debug mode. We don't need this behavior anymore because we have implemented native functions. So the programs. What's the difference between problems and programs? I mean, programs are problems. They create problems. So the programs can't print their results themselves. Does that make any sense? I think it makes a lot of sense. All right, so the next thing is introduce BM, like printf64 native function. So that's kind of cool. It's going to be 5. Introduce printf64 native function function to BME, right? So, okay. And the thing we're doing here, we're using print F64 to print results of eBASM and PyBASM examples, not PPy. So the problem is that like in Russian language, the number pi is called P. I know, very funny, ha ha ha, P joke. But yeah, so use print F64 native function in eBASM and PyBASM examples. Okay, I'm gonna push that right into the repo. How many times did I say P instead of pi? Because I don't even think about it. In Spanish, it's called P2, like the way you pronounced it. I see. To be fair, it feels like in a lot of other languages, pi is also called P, and it feels like only English calls it pi for some reason. I don't know. I don't know. I love Russian. I'm learning it with Duolingo. Nice. Good luck with learning Russian. What is your native language, by the way? I'm asking because I just want to know how easy or difficult it would be for you to learn Russian, right? If you already know other Slavic language, probably learning Russian is not going to be that difficult for you. But if English is your native language, it could be kind of difficult. Persian. Interesting. I don't know how difficult this would be to learn Russian for Persian. If you know other language, you will need is alcohol to speak Russian. It's Persian. I know nothing about Persian, but maybe it would be difficult to learn Russian because definitely you will need a different alphabet. But learning like Cyrillic alphabet is actually the easiest thing about Russian. The most difficult thing about Russian is the grammar, right? But even with the grammar, to be fair, like to communicate with Russians, you don't really need that much of a grammar. You just need words. And if you just say words without any grammar, people will still understand you. You're just gonna be sounding weird. But anyway, so let's continue. So what else did I want to implement? I wanted to implement something else. Oh yeah, I wanted to implement. I wanted to implement the other printers for different things, like print I64, U64, and print pointer, so you can print different kind of things. In English line of a company I worked at, learned how to read Cyrillic on the plane ride to Bulgaria, which is like 4 hours. Yeah, so which actually confirms that learning Cyrillic is not the most difficult part about learning Russian or Bulgarian or any Slavic language that uses Cyrillic. So yeah. To be fair, if you visit in a country that uses Cyrillic, just learning how to read Cyrillic is going to be very beneficial, because in languages like Russian, we still have a lot of borrowed words from Latin and like German, French, and English. We just spell them with Cyrillic. So yeah. So, and if you will be able to learn Cyrillic, some of the words will be familiar to you. You just need to learn the alphabet. All right. Yeah, let's implement some printers. BME.c. And you know what? Some of this stuff. Этот ссылок. I don't know what that means. I don't speak Russian. By the way, Prince 537, are you talking about this stream? So it's because what Prince 537 said is this is a circus, and I presume that you said that about the stream. So yeah, I appreciate that. All right, I want to extract all of these things to a separate like module, which we can call BM standard library. but maybe a little bit later. So the thing I want to do here, I'm going to introduce static error BM print I64. I'm going to BM. Streamer, not a clown. I mean, I kind of am. I'm kind of a professional clown with programming skills. It's like a specialized clown for programmers, right? Because programmers probably don't like to go to a circus, right? So they need a specialized circus. Yeah. So how do you do that? PRIU, and there's probably PRID. Okay, and PRID64. Thank you, iPave. Thank you for liking me. I'm gonna sneeze, by the way. Am I? No, I'm not gonna sneeze. Debated, by the way. So this one is gonna be I. So this is gonna be just I. So, and push. I64 is gonna be 3. Cool. The next one is going to be U64, and I think I can easily implement that by doing something like and then instead of D64 I can do U64. Cool. Then I'm gonna go here, and now we have U64. It's gonna be for the fourth one. It's gonna be the fourth one, and yeah, BM print. Let's go back. And the last thing, we already have all of the printers, right? We already have all of the printers, and the thing I want to do here is just static BM print PTR. Just print PTR. I could have actually just copy pasted the whole body here, right? Nothing particularly special, the whole body. And this is gonna be what? It's gonna be just PTR. There we go. We have all of the printers for different kinds of stack frames, depending on what on how you want to interpret all of that. So this is gonna be PTR, and this is gonna be 5. And you kind of need to know all of these things, and this is exactly why I wanted to have this external expression, so you don't have to like keep track of all of these numbers and stuff like that. Keep in mind that this is like an early stage of native function calls. In the future it's going to be a little bit more convenient to work with, hopefully. I don't know yet, we'll see. Anyway, just macro everything. Okay, so here's that. Let's try to compile all that and see if it compiles. But yeah, moving all of that to like dynamic libraries would be so fucking cool. But at the same time, starting to use dynamic libraries will result in a very like non-portable code, right? Because right now this thing probably works on all of the major operating systems because we're using only like standard C library. Once we start using like dynamic stuff, we'll probably have to abstract away working with dynamic libraries here. It's like abstract away from Linux, Mac OS, Windows, and stuff like that. Denise was bitching about memory handling macros going 5 levels deep in ISC bind. Thank you, Prince. Thank you so much. And also different ABIs. Yeah, it's gonna be fun. And it's probably completely unnecessary because the use case for this virtual machine is that it's supposed to be a library. So you use this virtual machine in your project. You link with this library and you link with your program, and your program have a virtual machine that you can work with. What's the benefits of using dynamic libs here? We don't know yet. So that's the point. That's what we call research. Right, so we are exploring what's going to be the benefits. It's kind of interesting, like people ask these questions, but we're literally going through the research to answer this question. Is that It feels like majority of people don't realize that some questions take several days to answer, right? Because usually in real life, people get used to the situation when they ask a question and they instantly get the result. But the reality is that some questions just literally take several days to answer. And this is one of the questions. What's the benefit of using dynamic libraries here? I don't know. We spent like 4 days already trying to figure that out. And we're still not there yet. So we're still researching. It is what it is. And it isn't what it isn't. I'm gonna make a cup of tea, by the way. Does anyone have any questions while I'm making a cup of tea? Worst part of that, doing something for 2 days when then realize it makes no sense. What's interesting is that, here's the interesting question. Would you realize that it doesn't make any sense without spending 2 days? Would you be able to gather that information without spending 2 days? If no, that means you didn't waste these days, right? So that means you gathered information. So next time you won't waste 2 days on doing that. You know what I mean? So when you're doing something and it turns out to be not what you want, don't treat it as wasting time. Because while doing that, you gathered information. Now you know that it doesn't make any sense. Before you started this process, you didn't even know whether it makes sense or not. You see what I mean? Mm-hmm. It feels like, it does feel like it, but you have to treat it differently, you know? All right, I'm gonna make a cup of tea. Does anyone have any other questions? First DLLs, and next implementing NT-kernel in VM, then adding telemetry. I don't know, like, this is like a huge jump, like between NT-kernel and adding telemetry. Like, I don't know, there's some, like a lot of stuff has to happen in between these steps, in my opinion. I'm glad you said that. I was telling the same thing to a manager that answers sometimes need some days this morning. Well, you're welcome, and this is, by the way, is the reason why I'm unemployed, because I was also keeping telling that to managers. Good luck, good luck. Today's is kind of nothing. Some explosions sometimes take 2 months. Exactly. What's the cool program you use to zoom in the screen? It's called Boomer, and I'm not even joking. This program is called Boomer. Guess why it is called Boomer? Because it's a zoomer. You can find it here, by the way. It's written in NIM. So we don't have any executables for this program. The challenge is, to use this program, you have to build it yourself. That's right. To use this program, you have to prove that you're worthy of this program. Can you prove it? Build it from scratch. It's actually not that difficult to build. You'll have to download the NIM compiler and suffer for a couple of hours and then build it. It's actually nothing. We are working on this project even like longer than you will take to compile this program. So don't worry about that. Alright, does anyone have any other questions before I go to the kitchen and turn on my kettle? Maybe it's a reference to Boomer Bubblegum. No, it's a reference to Zoomer. It's called Boomer because it's a Zoomer program. It's still better than Rust, which you can't even build anymore without Rust C. Yeah, probably. Alright, I'm going to the kitchen. I'm gonna quickly turn on the kettle. It's gonna be super quick, like 30 seconds. Don't go anywhere, or you know what's gonna happen. My bot will automatically detect that you close the tab of the stream and will permaban you from this channel. Don't go anywhere. Hello. Hello everyone, hello. I'm back. To back. All right. So what do we got? What do we got? So we have all of these printers and shit. And what I want to do now, I want to go through all of the examples and use printers there. So, for example, we have this thing that just sums up 3 numbers. And it would be nice to just print the result of the numbers. All right. So src_bme, and where are the native functions? So what we need to do here, we need to print f. So the native is going to be 2. Okay. The next one. So it's going to be native 3. Alloc. So we're going to do what we're going to do with alloc. Okay, this one is interesting. So I want to actually print the number, the pointer, but if I try to print the pointer, it will consume it. So what I need to do here, I first need to duplicate the value on the top of the stack, then do native 5 to print the pointer, and then do native 1 to free the pointer. So this is how it is going to work. So yeah, we're getting really close to a machine with only a single instruction called native. So yeah, native 0, native 5, native 1, and yeah, it's pretty cool. So in E, we also use native Fibonacci. Oh my god, yes. I completely forgot about the famous Fibonacci example. Yes, I'm not... Okay. I think we need to rewrite this example because, first of all, I want to have limited amount of iterations here. And also, while I'm iterating through the Fibonacci numbers, I want to keep printing them, right, at some particular point. So yeah, I'm gonna put the to-do here. To-do, rewrite, sage mode, rewrite fib BASM example, right? So first of all, what I want to use here, limit amount of iterations, print the generated numbers on each iteration. There we go. So this is essentially what we need to do here. Okay, and I'm not gonna go here because it's implemented this way because it was the first example pretty much that we implemented, so the machine wasn't able to do much, right? It wasn't able to do much, so that's why it's kind of a lame example. So we don't need to have that anymore. So here's the BASM. Oh, that's cool. That's fucking cool. So you know what we can do now? We can actually print all of these things. So that means I can do dupe 0 and then do a native 2. I think 2 is the thing that prints the float. Yes, it does print the float. So essentially we do that, then we call lerp, duplicate that value, and to be fair, do we really need to do that? We don't. We can just consume it right away. Right, we can consume it right away, and then native 2, and then native 2. There we go. So we're just using lerp, and lerp is implemented entirely in BM bytecode, entirely in BM bytecode. And this thing probably would be a pretty cool candidate for like JIT compilation and stuff. Imagine actually translating that to a very performant like x86 instructions. And it shouldn't be that difficult. Shouldn't be that difficult since we know. Yeah. Oh. Yeah. Okay. Cool. So here's the lerp, and in BASM we're gonna have that. Cool. JIT and shouldn't be that difficult. Yeah. So it could be kind of difficult because x86 is kind of painful to encode and stuff like that. But I have a couple of ideas on how we can simplify the process of coming up with a JIT compiler for x86. Also, maybe maybe we could start with implementing a JIT compiler for something more simple, like RISC-V. But it means that I'll have to test it somewhere, so I don't know. What is your workaround for dynamic leaps? Do you use Docker for isolation? Ooh, I don't know where to start. What do you mean? I think my kettle is ready, so I'm gonna go to the kitchen one more time and pour myself some water. And then I'm gonna go back. Don't go anywhere, or I'm gonna wrap all of your dynamic libraries in a Docker container. I know how to do that. I'm gonna do that. Don't go anywhere. What? Hello. Let's continue, boys and girls. Let's continue. Let me see. So I updated all of this stuff. Let me recompile the examples. All examples compile. And the thing I want to do now, I want to go through all of them and just see if they work correctly. Right, so I'm going to start with 1, 2, 3, F. So it's going to be BME, example 1, 2, 3, F, BM. So it does print 6. This is exactly what we expected for this example. Next one is going to be I. It prints 6, but integer. Cool. Now, the next thing is allocation. So the only thing we expect from this example is to print pointer. And here you go. Here's the pointer on which we allocated everything. And it also deallocates everything. So if I do something like while grind, it will say that we didn't leak anything. No leaks are possible because we also freed the memory. Okay, so the next one is going to be E. So E should compute the E number. All right, so I want to get rid of the val grind. Yeah, there we go. Oh yeah, by the way, as far as I know, val grind is x86 emulator. So it's running your program in an emulation. So we have a program running in BM virtual machine, running in x86 virtual machine. How about that? Isn't that amazing? I think it's kind of amazing. Okay, Fibonacci doesn't work right now. Right now it's gonna actually go indefinitely, so it's not gonna. Yeah, it's actually will Stack Overflow because it goes indefinitely and consumes the whole stack. So it's not gonna be working right now, and this is one of the reasons why I put it to do here. Right. The next example is gonna be lerp. Right, lerp, lerp, and it prints all of the lerp examples. Actually, I want the lerp to be a little bit more interesting. I want you to sample lerp at different intervals. So maybe this is something that I'm going to actually put here. So I'm going to put it to do. Make lerp BASM example more interesting. Sample through the lerp with regular intervals, something like this. Okay, and it's going to be a separate issue. And let's take a look at the pi. Let's look at the pi example. And pi example should be working. It actually takes some time because it's in val grind. Holy shit, it's so slow in val grind. I wonder if I run it without the val grind. Yeah, it's actually way faster. Holy shit. But yeah, it's just computed this thing. All right, so I think we're ready to do all that. Now, I want to commit this thing. 5, extend the native function environment of BME. So what did we do here? We edit these functions here. add, edit, native functions. I'm gonna do something like this. It's gonna be this, like this. Cool. Might as well actually do something like, it's too much. All right, I'm gonna push that right into the repo. Push that right into the repo. And then I'm gonna also commit all of these things. Make examples use native printers to output their results. There we go. I'm gonna push that right into the repo as well. All right, we're done with this issue. The issue was to introduce native functions into the virtual machine, and in fact, we already have native functions. Isn't that amazing? Now we need to expand on that idea, and to expand on that idea, I created a bunch of separate to-dos, right? And yeah, so let's go ahead and create a pull request. This is amazing. I'm really happy with how it turns out. Your Emacs font is getting bigger every day. Just like Mom. Sorry. All right. So introduce. By the way, hello, Belgian. Welcome to the stream. I'm sorry. I'm so sorry. I couldn't help myself. I should stop watching Forsen. Because of Forsen, I cannot stop making your mama jokes. It's so dumb. I used to learn and code C language to clear in interviews where they ask you to find the output on paper, then transition to Python, then to C++. If you learned C primarily to crack interviews, I think there's something wrong with our industry. That's the only thing I want to say. By the way, Belgian null. Like I don't know when you joined, but we actually have pretty cool progress on native functions and shit. All right. Humanity doomed. Finally. I hate humans. I hate. All right. Introduce native function mechanism. And let's actually close this issue. 5. It's actually 5. Thank you very much. eLisp interview. Interesting. That's a lot of commits. Holy shit. And not that many changes though. Look at that. It's not that many changes, but a lot of commits nonetheless. Alright, so we need to snitch up all of the to-dos. It's gonna be snitch, report, prepend, body, introduced in 31. Cool. So rewrite fib BASM example. Yeah. So limit amount of iterations, print the generated numbers on each iteration. Cool. External native function declaration for BASM files. Cool. Make lerp more example more interesting. Some sort of mechanisms to load native function from DLS. Cool. So we're gonna report all of these to-dos as issues, and I'm gonna push that right into the repo. As you can see, all of these to-dos became issues that we can finally work on. Isn't that amazing? That's the future of software development. You think IDEs improve your performance as a developer? No, this kind of shit improves your performance. I was in an interview once and the interviewer was looking at the YouTube videos on his phone while I was answering stupid technical questions. God damn, holy fuck. This is basically the essence of the technical interview. Holy shit, nobody gives a shit about. Our industry is so fucked up. Holy shit. And this is, by the way, the reason why I'm unemployed. I just don't want to be part of this circus anymore. Holy fuck. I'm just waiting when that bubble is gonna finally burst. Like, when is it gonna burst? And when it's gonna burst, it's like everyone is gonna be fucking suffering. Yeah. Interesting. Alright, waiting for macOS. What about creating your own company and dictate your rules? No. Okay, so here are the changes. To be fair, I kind of want to work on this on these issues that involve coding in. By the way, did I merge the previous pull requests? Oh, okay. It's make file adapt to make both Berkeley and GNU make compatible. Oh boy! Oh boy! Oh boy! Oh boy! I made the changes to make file, so it's still not PostFix, but at least it runs with both make flavors. Oh, that's interesting. You want rebase? I would really appreciate you if you rebase after I merge it. Thank you. Thank you for submitting that. I'm actually okay with this solution. I'm totally okay with that. As long as it works exactly as it worked before. So yeah, thank you. Thank you so much for thank you so much for dealing with my GNU extension addiction. So yeah. Hi, new here. I'm about to dive in Vim as an editor. Should I better use Emacs? Big differences. I think you should use Visual Studio Code. Like, I mean, it's 2020. So if you're learning programming today, just use this thing. Just don't worry about Emacs, Vim. These are dead editors. Nobody uses them. They're for these lost boomers that are not hired to any companies anyway. So just use this editor, right? So and you're gonna be fine. Don't even worry about that. Seriously, don't waste your time. So just use Visual Studio Code, and also program in JavaScript. JavaScript is a good language. Trust me, I programmed in it. Made a lot of money with it. So yeah, so we're ready to merge this thing. Delete the branch. I went to an interview at an Erlang job and they turned me down because I couldn't answer some stupid quiz about people wearing color tests. Classic. It's kind of sad though, but classic at the same time. Yezu, kawaii desu. Dynamic programming. Yeah. Okay, so how about we program in assembly a little bit, chat? So because I want to kind of work on this like lerp and rewrite fib BASM examples. So let's actually program in assembly a little bit. I think it's gonna be cool. Bassembly. What's up, Gabriel? Hello. Welcome to the streamers. I don't remember if I said hello to you, but hello. All right. So what's that? Ooh, 32. So this is the 32nd issue, right? 32nd, and this is Fibonacci. Right. So here's the Fibonacci example. All right. So let's actually use shmod. By the way, Heroes and Plots, could you please ping me when you rebase the pull request? If you're gonna rebase it right now, right? Maybe you're gonna do that later, so I can look at it on the stream and merge it on the stream as well, because maybe I can forget later, but maybe I won't forget later. Anyway, so what I want to do here, I want to introduce the main. So here's the main. I'm gonna remove all of this nonsense. We don't need it anymore, and then I'm gonna do GMP 1, so this is the entry point. GMP mining. Okay. Okay. So this is how we're gonna do all of that. So initially it's up. Okay, thank you. Let me see. Oh my god, it's so slow. Oh yes, thank you so much. This is super cool. Super cool. We also need to wait for... It's perfect. Okay, let me take a look at it one more time. Hot and fast. The fastest rebaser on the West. Why did you add clean? We don't need clean in 2021. We don't need clean in 2021. Okay. All right. I'm gonna merge it because I'm lazy. I'm lazy to remove it. Okay. Looks good to me, but I don't like clean but I'm too lazy to remove it. Feels bad, man. So thank you. Thank you for contribution. Okay. Thank you so much. Okay, my position is, I think I actually explained that position several times already. I need to make like a blog post, so every time we talk about that I can just redirect to that blog post. So is there a clean... Here it is. Oh my god, it's so slow! Why is it so slow? Alright, so here is my position on clean. Yeah. So it's explained here. So if anyone wants to know my position on git clean, on make clean, it's there. All right. Nico seems to like FreeBSD. Yes. Nico, do you like FreeBSD? It's a very dank operating system, not gonna lie. Okay, so what we're doing here, we're pushing 0 and 1, right? We're pushing 0 and 1. And essentially, FreeBSD, yes. Good damn it. I guess we'll have to first print all of these things. We'll have to print all of these things. I hate make files without a clean target. Well, it's understandable. But at the same time, clean target is something that you have to maintain all the time. It's just... but anyway, whatever. Doesn't really matter. It's like arguing about like tabs versus spaces. So I stated my position about make clean, and it's out there, and that's it. So yeah. Okay, so here we print first two numbers of Fibonacci sequence. Then we push these two numbers here. Right, then we just push them. To be fair, maybe we don't have to do that. Let's start with something like this. So I'm just thinking what could be better to evaluate here. Right. So 0, 1, and the counter. Right. The counter is going to be how many of them we want to generate. Let's say we want to generate 100 of them. Right. We want to generate 100 of them. Cool. So this is the F0, F1, N. So the amount of iterations. Amount of iterations. Cool. Then we start with a what? So I'm gonna be consuming this value anyway, right? I'm gonna be consuming this value anyway, and because of that, I probably need to swap it. So it's gonna be 0, 1, 2, So I'm just gonna do a swap 2, and that essentially does this thing. Maybe what I want to also do after I swapped it, I want to dupe 0, effectively duplicating this thing, and then printing it right away, like this. Printing it right away, which will result in consuming it. So this way I will actually print all of the necessary Fibonacci numbers. Alright, so after that, I suppose I need to duplicate the previous value here by doing something like dupe 1. That will duplicate this thing and put it on the stack here. Right, and put it on the stack here. Then I need to do something like plus I, which will sum it up. This is not particularly convenient to see, actually. I don't really like specific numbers. Let's try to do that slightly differently. All right, let's try to do that slightly differently. I'm going to be pushing things like F0, then F1, and then N. This is exactly what we do here, right? So then we do swap 2. So that means it's 0, 1, 2. I'm swapping them. There we go. So we have that. Then I'm duplicating F0. Then I'm printing it. Then I'm duplicating 1, which is duplicating these things and putting it here. And then I sum them up, right? I sum them up, and this is the result here. Cool. That's pretty interesting. So after that, I need to decrement n. Why jump main at the start? Because it's an official boilerplate with BASM, because I may have additional functions defined here, right? And and the execution always starts at the top, so I'm skipping it right to the main. So I can probably move them here, but it's not particularly convenient in my opinion. I kind of like to have them at the top. All right, so after that, I need to decrement n, right? So what I'm going to be doing here is swap 0, 1, 2, swap 2. This is swap 2. Like this. Swap 2, then I'm gonna be pushing 1, right? And minus I. I think minus I has to be actually plus I, and minus I should be renamed to add and sub, in my opinion. Right, then I do minus I, and that results in that. And this is kind of the problem. Because I need to swap these two elements. I need to swap them somehow. So that means I do the fucky wacky. I'm pretty sure there should be like an easy way to do that, but yeah. So when we push in so this thing has to be here, right? Instead of that. But anyway, so how can we do that? If I can do something like swap 2. Swap 2, there we go. Then I can do something like swap 1, right, which will swap it like this. And then I can try to do swap 2 yet again. And did it work? I think it worked. So because smaller at the bottom, then bigger one, and then minus 1. Cool. After that, I need to push some sort of a value, right? Push 0, and then I can check if it's equal to 0. and then if I negate it, jump if it's not equal 0. There we go. So that should be it, actually, I think that should be it. That's kind of a scuffed implementation, but yep, I guess. Do we even have not? I don't remember. I think we do have not. Yeah. So let me rebuild everything here. Yep, and then all of the examples. And yeah, it does compile. What the fuck? Holy shit. So it seems to be working. So this thing will keep generating Fibonacci numbers and also keep printing them. And then we can control how many Fibonacci numbers we want to generate, like with this number, because it's like a counter. Yeah, I don't really like that I have to do this switcheroo here. I think it could be optimized somehow better, but it is what it is. Alrighty, so let me see. I'm gonna do the BASM. Examples, fibs BM. Looks correct, looks more or less correct. We can take a look at how it works in BME in the debugger. Okay, so push 0, yeah, push 1, cool, push 100. So here they are on the stack. We pushed all of them on the stack. Swap 2, so we swap them around, duplicate. Oh yeah, so the top of the stack is actually here, I think. Native 2, and that printed it. And am I using, yeah, I think I'm using, so I think this one has to be F actually. This one has to be F. Yeah, so here's the thing. These things has to be floats. This thing has to be floats, and this thing has to be integer, and you have to constantly keep track of that. So this is a plus F, so then swap 2, push 1, and minus I though, right? Then push 0, Q, and not, and so on and so forth. So yeah, because the counter is integer, but the values, the Fibonacci numbers are, well, they don't really have to be, like we're not doing any floating point arithmetic. Yeah, we don't do any of this shit, so that means I can also use plus I here. So, and if I'm going to be printing all of that, I need to print it as 4, so let's actually do native 4. Yeah, there we go. Alrighty. Oh, what's up on both? Cool. So this entire stuff compiles, but I also need to recompile some of this stuff. Maybe I don't have to. I don't know why I keep recompiling all of that. Okay. So let's take a look. We're pushing all of that. 94. It printed 0. Then we keep swapping things around. Not 0. And jump if. Oh shit. Yes, we did a fucky wacky and probably an oopsie doopsie. Alright, so let's try to understand where the fuck the problem happened. So we push F0, then we push F1, then we push N. Swap to 0, 1, 2. So we swap them, so this becomes like this. Duplicate 0, we duplicate it. Native 4, we print it. Then we dupe 1, so that means we dupe it here. Then we sum them up, like this. Then we swap 2, right? Actually, at this point, I think we should first swap 1, right? Swap 1, like this. Swap 1. And only then swap 2. So that will result in this kind of thing. Swap 2. Then we push 1. And I think I found a mistake, because we need to do swap 1 yet again to actually properly subtract things. And then when we do something like this, it will be -1. Cool. So first is smaller, then bigger, then the next one. Okay. So I think after that, we don't even have to do this thing because we already put everything in place. Then I push 0. Then I push 0. And this is another mistake. I think before pushing 0, I need to duplicate 0. So this is gonna be this is how it's gonna be done. Then push 0 is gonna be 0 like that, right? Then equality is gonna consume both of them and produce false. Then not is gonna invert false into 1, and then jump if will consume 1, resulting in the next iteration being correct. Okay, I think it actually works. So this is the final solution without any swap bullshit down below, because we actually resolved all of the swappage here, I think. So yeah. Looks good. Looks good, I think. All right. So let's go. It seems to be compiling. I want to also take a look at the BASM examples of fib BM. Cool. Looks okay. And let's try to debug all of that. Okay, we're pushing everything onto the stack. Okay, so here are our parameters: fib0, fib1, and n, which is 100. Cool. So we're swapping this stuff. We're duplicating. And then we're printing. So the 0 was printed successfully. Then we duplicate 1 yet again. Then we sum everything up. Everything has to was summed correctly. Then we're swapping something. Swapping again. Swapping again. Subtract. Fuck. I think I didn't have to do the swap. I think I fucked up. Yeah. Okay. Swap before minus wasn't necessary, I think. Swap before minus wasn't necessary. Alright. Then, yeah, so it resulted... I mean, here's the interesting thing. This is a single stack frame. It's a single value. And these are 4 of the interpretations of that number. So it's just a single sequence of bits. It could be interpreted as U64 as unsigned this value. As signed, it will be interpreted as -99. As float, it's going to be none. And as pointer, it's going to be this. Right, so essentially, we have different instructions that treat the stack frames differently. Right, so you can actually put, like push an unsigned integer and then treat it as a float with floating point instructions. Does it make sense? So, and our debugger basically shows different interpretations of those things. Like you just can interpret them differently, depending on what you're doing exactly. All right. So, I did a fucky-wacky, yes, yet again. But it's kind of fun actually to work with this machine. Not gonna lie. All right, let's try to do that one more time. 0, 1. We'll keep pushing all of that, and then 100, swapping things around, printing, so this thing has been print. Duplicate plus I, swap 1, well, we swapped 1 with 1, so nothing special. Push 1, then minus I 0. Oh, okay, that's kind of dumb, but yeah. Okay, then we duplicate, then we compare it, not 0, 1, jump again and swap to... I think we did it. I think we did it. So the next iteration will be more or less correct. Okay. Oh shit, it's working. All right, I think it's working. Now look, look, look. Without the debug mode. Shit. Well, it kind of worked. It kind of worked. And I think the reason why it worked, well, we don't halt, but I mean, I don't think not halting. Oh, I see. A legal instruction address. I see. So it actually went over. I think like 100 Fibonacci numbers is kind of too much. So yeah. Okay, so let's rebuild everything. And if I try to do this thing, yeah, there we go. We calculated 100 Fibonacci numbers, which actually overflowed the integer anyway. So I think it was too much. So if we like slightly change it to maybe 10, I think 10 would be better thing. But yeah, there we go. Here's the 10. Maybe something like, is it really 10? 0, 1, 2, 3, 1, 2, 3, 1, 2. It's actually 10. It's actually 10 of them. Let's make 20. Yeah. Okay, 20 is a little bit better. Maybe something like 30 would be even better. There we go. So now we have a program that basically computes and prints out Fibonacci numbers, and it's implemented purely in our virtual machine, and it's like actual proper program that interacts with operating system and stuff by using native functions, right? So the only thing we provided to this program is an binding to a native function that prints unsigned integer, and that's it. So this thing just keeps generating numbers and just calls to this native function and prints them out. So this is the whole thing here. And it's actually pretty compact and pretty small. And yeah. Isn't it cool? So this is basically what I wanted to have. And it just prints and Fibonacci numbers for you. All right, and how quickly it does that? It's actually pretty fast as well. Yes. This is how fast our virtual machine is. Like it generates like this Fibonacci numbers. It's pretty cool, huh? I think it's pretty goddamn cool. Yep. And we don't even have to like dump the stack to like understand what's the output of the program. The program itself can interact with the operating system through the native functions and just print all of this stuff for us. Yeah. Slowest part is the output. Yes, exactly. Slowest part is the output. But we don't even compile with O3 as far as I know, right? We don't even compile with O3. Yeah. So if we try to compile everything with O3, it actually takes a little bit more time to compile. And then examples, will it be faster? Probably won't. Oh wait, look at that, it's even faster. 100 milliseconds. Not 100 milliseconds, 1 millisecond. But can it call write syscall? Well, if you create a binding, it will. Seriously, it will. Since we have the native, native interface, like you can do write, I suppose. Not even sure how to fill up a string. This one is really interesting. For example, if you want to like put a string into the memory, how do you do that? Well, so far, if you have a thing, if you have a function that can access a single byte in the dynamic memory, you can iterate through, you can just, iterate through the string and push character by character, which is dumb. So we need some sort of like a memory buffer, like static memory buffer within the virtual machine, into which we can put strings and stuff like that, that later we can copy into dynamic memory and eventually call write syscall if we want to. So yeah, virtual machine needs some sort of like static memory buffer, which will be part of the executable as well. Yes, I think that's what we need. Does it make sense? I think that will be actually kind of cool. Yeah, it will be primarily for string literals, but maybe for anything. You will be able to store there anything. Yeah. Just some additional static memory specifically for this kind of stuff. Sounds good, I guess. We'll see. All right. Yeah, Elf does something similar. Elf does something similar for sure. Okay, so let's do a compilation. So here what we do, all right, so this is what we've done. 32 improve fib BASM example. All right, and I'm gonna push that right to the repo. Also, I think I need to update the stuff here. So now we have more. Saved it already. More cool examples. So we have a Fibonacci example. We have E computation example and pi. Do we have any other cool examples that we can show off? We have a lerp, but lerp is not that interesting anyway, so yeah. So I suppose Fibonacci, E, and pi are the most interesting examples. So and these are the examples that we want to show off. 32. Update readme. So I'm gonna push that right into the repo. Void. Did I do void? God damn it. I think I need to fetch the latest changes because I merged the Hertz and plots commit, so I need to be a little bit more careful with this kind of stuff. Yeah, there we go. But I don't think I will conflict with any of these changes because I don't think I modified makefile anywhere here. I only modified the Fibonacci example. Yeah, I can actually just create a pull request and without rebasing or anything like that. Without rebasing or anything like that. I did remove all three. But why did you do that? Your program is slow now. Okay. Improve fib BASM example. What do you mean by trigonometry? You mean we need to introduce instructions for trigonometrical functions? We can introduce them through native functions, so I don't think it's that important. Approximate cosine for x. We can map cosine to a native function, just use it. But maybe, I don't know. Maybe it's not that interesting. Okay. Alright. It's a pretty good example. And another thing I want to implement, I want to improve the lerp as well. Easy 10-line assembly program. Yeah, pretty much. Pretty much. Fib BASM. Is it 10 line? Yeah, it's pretty much like 10 line, around that. It's not that bad for an assembly, to be fair. And the fact that we don't even have any registers is actually pretty interesting. Cosine will be a separate dynamic library. Yeah, probably. You could use some aid in writing debugging, perhaps a visualizer that shows what's happening every step. I know it's a bigger project. Probably, we'll see. So right now I'm focusing on implementing as many features as necessary for my purposes. So yeah. So the next important step is pretty much having a JIT. But I also would like to improve the usability of native functions, because using native functions is kind of pain in the ass. It's kind of pain in the ass. All right. So the next thing I want to implement, I want to make the lerp example also a little bit more interesting, because right now lerp, you know, just takes 3 samples, and I actually want to make n samples, right, with a regular step. So that's what I want to do. Let's implement that. So right now lerp, so here's the lerp example. It's like this. Here's the lerp, and that's what we do here. All right, so we have A, B, and T. Yep. And what we need to do. Oh, also we have will lack a lot of important instructions for comparison and stuff like that, so I probably will have to do that. Let me go to the BMH. So the instruction set is not stabilized for sure. We lack a lot of stuff. Like, we don't have that much for comparison. Okay. Comparison instruction set is not complete. So this is something that we'll have to fix at some point, that's for sure. All right, so let me create a separate branch for this thing. It's going to be 34. 34. And let's go to the LERP example. BASM. Cool. I'm going to have A and B on the stack. So we're going to start with push 69, right? So this is going to be A, then push 420, this is going to be B, and then push, let's say N, which is going to be the amount of samples we want to take between A and B, right? We're going to iterate through this entire thing, and we're going to do a linear interpolation, if that makes any sense, right? Just to test things out. So, and let's take a look at this stack. So we're pushing A, then we're pushing B, then we're pushing N. And the thing is, I don't really care about N, right? So what I do care about is, oh yeah, this is kind of interesting idea. I pushed integer, but for arithmetic operations, I will need to convert it to a float. So, and we don't really have an instruction that enables us with converting between integers and floats. I think we'll have to implement that at some point. So let me add a to-do here as well. There's no operations for converting integer, float, integer. Yeah, something like this. We will definitely need this to have this kind of operations, because yeah, we have separate like sets of instructions to do all of that, to do floating point arithmetics and integer arithmetics. Yeah, I think this is kind of important. So, all right, and since we don't have these things, I'm gonna be pushing like floats right away. So, and another thing, what I need to do. I need to find the step. So to find the step, I actually need to first push 1. Right, this is going to be 1. So that means 1 is going to be somewhere here. Right, 1 is going to be somewhere here. And after that, we need to do something like diff f. Right, so we take the previous frame and divide it by the current frame. Hello, Dr. Puppy, welcome to the stream. All right, so we can do something like diff f, and yeah, we take the previous frame and divide it by that one. So that means the result is going to be something like this, and that is the step of the interpolator. Right, it's the step of the interpolator. Maybe it will also make sense to push the initial value of t. Right, so we have t here, which is going to be 0 here. It's going to be t. So a, b, and here we have t. I said t. It's not 5t. Right, and then we have this step. Right, and we compute it like this. So the reason why I'm completely like that is because then later I want to change it to something else, and I want it to automatically recompute everything. Alrighty, so what I need to do next? I think I need to remove all of that stuff, but maybe I'm gonna keep some of these things. No, it's not gonna be multiplied by that, because this multiplication is automatically done by the lerp. What's the point of having lerp if we have to do this multiplication ourselves? No. We're not doing that. It's done for us automatically. The only thing we need to do, we need to traverse from 0 to 1 and nothing else. Okay, so then we're gonna have something like a loop here, and then we're gonna do jmp if loop. Cool. So we need to, so if we push a b, that means I have to do a very interesting thing. I need to first duplicate a 0 1 2 3. It's gonna be dup 3 dup 3, and that gives me a, right? Then 0 1 2 3 dup 3 yet again, dup 3 yet again. This is going to be b, and dup 3 yet again is going to be a t, right? Because this is what we get in this particular order. All right, so that's actually pretty cool. Then I'm calling lerp mix. I'm sorry, Panapudi, but this is not JLSL. Hello, by the way, how are you doing? Okay, so lerp. So we call lerp, and as far as I know, lerp is gonna actually consume all of that, right? It does consume all of that because it also cleans up everything, right? And at the end, you have the lerp result, right? So here's the result, which you can then print native 2. Let me take a look. BMEC. So 2 is print F64. Nice. Okay, so after we printed all of that, we ended up with this thing. And this is really interesting because all right, makes sense. What I need to do is I now need to decrement t. To do that, I need to swap 1. So by doing swap 1, I'm swapping these two values like that. But then I need to do dup 1. Right, I need to do dup 1, which will bring this thing here. And after that, I need to do minus f, which will subtract the top value from here. Actually, it has to be plus, because we're iterating from 0 towards 1, so it has to be something like this. Right. And then we have to swap 1 yet again by bringing everything up. There we go. And we actually repeated the cycle. So we are at initial position that we were. If you go through this first initialization, like first initialization, not initial initialization, you end up with something like A, then B, then T, then 1, then N, and then you squash them like this, and you end up with this. So this is the state before a single iteration. This is the state after the iteration. So you see, we went back to the original state, but with t plus 1 over n. So, and we're gonna keep repeating that until t becomes greater or equal than 1. So, and this is something that we have to actually check. We'll have to push 1 onto the stack. So we pushed 1, right? And then we have to issue an instruction that is called GIF. Yes, that's the actual instruction. We have an instruction called GIF. What did you mean by don't donate something to buy something? I meant like, for example, I don't have a good microphone stand, so don't donate me to buy a new microphone stand. Something like that. I don't like obligations put on me because of some money or something like that. I don't like to be owning anything to anyone. All right. Cool. Greater or equal. Okay, so we put 1. Oh shit, this is actually... So before pushing something like 1, I think I need to duplicate this value. So I'll have to do something like dupe 1, and I'm gonna be duplicating it here, and then we're gonna do push 1 that pushes 1 here. Right, and then we do Jeff. Right, then we do Jeff. It's greater or equal. So if this thing is greater or equal than 1, right, I think this is how it does that. It takes the previous thing and checks whether it's greater or equal than that one, right? So, and if I take a look at this thing, inst Jeff. So this is BMH inst Jeff. Okay, so, oh, that's interesting. If the top greater than or equal, I think there's something fucked up here. I think there's definitely something fucked up here. Top is greater than equal. Yeah. Okay, so there's something wrong with the semantic. I will have to look into that a little bit later. Okay, so greater than equal. If that thing is still greater than equal, then we're gonna continue. So this will result in 1, and then doing jump if will also consume this thing and repeat the cycle. So technically we finally finished all of this. So this is lerp, and it basically iterates like lerps, linearly interpolates from 69 to 420 with 10 samples, hopefully. So that's it, I think. And I need to put a reminder for myself. Because, for example, if we do minus, you actually take inst minus, right? Minus, you take the previous frame and subtract the top one from it, right? So first argument is the previous frame, and the current argument is the top frame. So, but in Jeff, the first argument is the top frame. Okay, so this is definitely some sort of a bug. Inconsistency between Jeff and minus instructions. Right, so we're gonna put it to do here. So, and then we'll have to fix that later. Okay, let me compile all of my toolchain first, just ensure that everything's okay. I didn't really modify anything in toolchain, but okay, cool. So here's that, and I think I'm ready to take a look at the lerp now. So here's the example, here's the lerp, BM, and that's actually a pretty big program. Look at that. Yeah, this is the whole lerp. Like, this is all the instructions of the lerp. And people asking why I'm doing jump 1, right? So here's a pretty good example why. Because I want to have lerp at the top, but main at the bottom. And literally there's no reason to do that, but I just like got used to that while programming in C and stuff. So, and that's why there's always jump main. If I add more instruction at the top, it gets updated. So it basically jumps to the entry point of the program automatically. So yeah, I kind of like that the examples we're working with are getting more and more complex over time. That means the machine is evolving, so it can do more interesting things. Yeah. Also, I think we need to start running these examples on CI. So I want to create in this thing as well. Why not an entry point? Because more work. So to add an entry point, that means I will need to add modifications to the assembly. And with this thing, I don't have to. I just do jump main, and the virtual machine always starts at 0. So it's just less work. Like it already worked. So the problem is solved. Yeah. So we always start at that, and you just jump whenever you want. Does it make sense? I'm a very lazy person. What can I say? It's just like it's a pretty cool solution. Did anybody ever hire you because of Twitch? Never. I'm doing that. Well, I'm streaming for 5 years, but I'm streaming actively on Twitch for 3 years. Not a single time. To be fair, there were some weird people that were trying to hire me in the chat. Oh, no. There was. Okay. There were some people who tried to hire me, but they were individuals, not the companies. Yeah, so it usually boils down to individuals who try to hire you to do their homework. So that's what you usually end up with. Yeah. So not a single company, of course, like not a single company, but a lot of individuals who don't want to do their homework. Job security. I don't know. I think I'm doing well to not take such jobs or such offers. All right. So here's the BASM. Let's actually try to run this entire thing. BME example lerp BM. If they don't know how to do their homework, they probably won't be able to do their job too. It doesn't matter as long as they pay me. What's up, man? Welcome back. So yeah. Okay, so let's see. So it's gonna be D, and let's try to see how it's gonna work. So we jump into 15. Okay, so push that. Here's the first thing. Here's the 69. Here's the 420. Then 0. Did I really push 0 there? Why did I push 0 there? Wait a second, that doesn't make sense. Ah, it's T. Okay, everything's okay. God damn it. Okay, so duplicate 3, do that, and then 0, then call 1, and I think we got that thing interpolated. Yeah, okay, that's cool. I think we got that thing interpolated. And dupe 3. All right. So then we print 69. And do we repeat our cycle? Oh yeah, we do repeat our cycle. Look at that. I think it works. All right, what if I try to execute that without any stuff? Oh shit, we got the lerp. So yeah, essentially we are interpolating from 69 to 420 with 10 samples, and it works. It just slowly interpolates. That's cool. And the lerp is implemented in BASM itself. So I can increase the amount of steps. For example, like have a 20 step, and the steps are going to be basically smaller, right? And if I try to recompile this entire stuff, now it's 20 steps, and it okay, so basically this step really, like, it's kind of strange. Something went wrong here. But I think it's like it overshoot at some point. That's probably what happened. Yeah, that's very strange. But with 10, it probably has something to do with like a Jeff logic here. Greater or equal. Why would it be like that? 11 samples. Yeah. Let's try to do 11 samples. Okay. Yeah, I guess it's if it's. So we keep incrementing t until t becomes greater or equal than that. I meant you had 11 samples. What I'm talking about? All right. So how many samples do I have here? 11 samples. Okay. Why is it like that? Float precision probably. It probably has some, but why is it so bad though? Holy shit. What about 100? What if I put 100 here? It's getting closer. Yeah. Greater or equal? Do we let it overshoot a little bit? And it's already too much. We can actually let it overshoot by a single step. Okay, that's very interesting. That's very interesting. We can try to let it overshoot by a single step. So at the top, essentially what we have... what the hell is that? Yeah, 0. I push 1. Okay. Duplicate 1. Then duplicate 0. Then wait. So I need to reconstruct the state of the stack here. Is it even worth it? Is it even worth looking into that? I don't feel like it's worth looking into that. So I need this state of the stack yet again. It's going to be A, B, T, 1 over n. Right, that's what we have here. And when we do dupe 1, we push in T on top of the stack, and then we push in 1. But instead of pushing 1, we can try to do dupe. Oh my god. Instead of pushing 1, we can try to do dupe 1 yet again, because 0, 1, that creates this thing. Then we can push 1 yet again, like this. And then we can sum them up, and that gives us 1 plus n, this thing. And then we do the Jeff. Right, so basically we incremented like by 1 step, and hopefully that gives us like enough room to properly implement all of it. I'm not sure if it makes much sense, but we can try. It's kind of dumb, but it is what it is. Yeah, it overshoots really hard. Overshoots really hard. Yeah, I'm gonna leave it as it was. So let me go back. So it's gonna be just like this, and the original one is gonna be just 10. I think it's just, you know, like floating point stuff. Will you add a table for the native functions so they can be referenced by name in the assembly? Yes. The native function mechanism is not finished yet. It's not its final form, so it's going to be more convenient in the future. Don't worry about it. Don't worry about it. I'm not some sort of a psycho that will force people to, you know, constantly look up, you know, names in the table or something. Like it's going to be done by assembly automatically. Don't worry about it. All right, so let's go ahead and do all that. 38, this is what I meant. Make lerp more interesting. So this was this thing, and we also introduced a bunch of to-dos. Comparison instruction set is not complete. There is no operations for converting integer float to integer. Inconsistency between Jeff and minus instructions. Is it really instructions? I think it's not about instructions, but rather their operand order. Inconsistency between Jeff and minus instructions, operand ordering, something like that. So, and let's actually create a pull request for our changes. So this is going to be the pull request for our changes. And yep. 34, and we're gonna report all of this to-dos. Beans niche report append body introduced in 37. There we go. So comparison instruction is not complete. Blah 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 blah. There we go. Let's report all of them. Here they are. All of them are reported, and if I report this thing, here it is. Now I can push all of that right into the repo. Right into the repo. Cool. So yeah, now our examples are a little bit more interesting. Maybe we can even remove some of examples, like 1 to 3 example is kind of meh, and a log example, but a log example is kind of important for, I know, for demonstrating. I don't know. So these examples 1 to 3 and a log are kind of dumb. So I think at some point I'm gonna actually get rid of them. Maybe that point is now? Question mark. Maybe that point is now, because these examples are more interesting. But you definitely need more simple examples, like 1 to 3. Yeah, I think I'm gonna keep them. All right. So let's wait until everything is done, and we're gonna merge that. All right, boys and girls, I'm streaming for 4 hours, and I'm kind of tired. Unfortunately, it's pretty much time for me to go. Thanks everyone who's watching me right now. I really appreciate it. Have a good one, and I see you tomorrow. Tomorrow we continue developing this thing, so I decided that we're gonna develop this project for 3 days a week, Monday, Tuesday, and Wednesday. So I'm gonna update the schedule pretty soon, and yeah, so I think it's gonna be pretty cool. I really like this project, so maybe it's gonna evolve into something meaningful one day. All right, so check out our the source code of this thing. Also check out our schedule for more information on different projects we're working on. So I'm gonna update it soon. It's gonna consist of VM for 3 days. Check out our VODs channel for archives of the streams. This stream is going to be there, but tomorrow we have a special playlist where I put all of the virtual machine streams. So if you want to follow the development from the beginning, you can find that playlist there. I think at some point I'm going to also link that playlist in the README of the project, so people can reference to it and just watch from the beginning. Also check out our Discord channel for offline discussion with the community. So yeah, that's it for today, boys and girls. Thanks everyone for watching. Love you.